Assalamualaikum, Prof. Bambang.
Waalaikumsalam.
Sehat, Prof?
Alhamdulillah, sehat juga ya?
Alhamdulillah, sehat.
Selamat pagi Bapak Ibu semua yang sudah join. Pak Khairul Irawan ya dari ULM.
Pagi Ibu.
Pagi Mbak Dewi.
Oh, Mbak Evi, selamat pagi.
Sukses acaranya Mbak Dewi.
Semoga, terima kasih.
Bagaimana operator, langsung dimulai atau mau di-setelkan video profil UNED terlebih dahulu?
Universitas Jember berdiri pada 10 November 1964 di Kabupaten
Volume
Jember,
video bisa diperbesar, volume video.
yang tersemat dalam sesanti Karyori Naras Ambuko Budi Gapuro Mangesti Aruming Bawono.
Cita-cita tersebut dituangkan dalam visi misi Universitas Jember, yaitu unggul dalam pengembangan sains, teknologi, dan seni berwawasan lingkungan bisnis dan pertanian industrial. Universitas Jember saat ini telah memiliki 15 fakultas, 103 program studi, 1.260 dosen, dan 33.928 mahasiswa. Selama 56 tahun perjalanan mengembangkan Tridharma Perguruan Tinggi, kini Universitas Jember menjelma menjadi perguruan tinggi terakreditasi A yang berada di peringkat 22 nasional dan telah memperoleh piagam penghargaan sebagai penyusun laporan keuangan terbaik ke-1 kategori Satker PNBP DIPA di atas 200 miliar. Berdasarkan analisis SWOT, Universitas Jember menetapkan tujuan dan sasaran strategis yang ditetapkan ke dalam tahapan-tahapan yang terukur di segala lini sumber daya yang dimiliki untuk meraih universitas yang unggul dan ternama di era revolusi industri 4.0. Mahasiswa Universitas Jember telah mengukir prestasi baik di tingkat nasional maupun internasional dan terus berupaya untuk selalu meningkat dari tahun ke tahun. Dalam sektor pendanaan, baik penelitian, pengabdian maupun publikasi jurnal ilmiah, terus mengalami peningkatan tren sehingga mampu mendorong tumbuhnya realisasi Tridharma Perguruan Tinggi. Di sisi lain, Universitas Jember juga meningkatkan kerjasama dengan mitra, baik dalam dan luar negeri. Alumni Universitas Jember telah banyak tersebar dan berkiprah di dunia kerja, baik di dalam maupun luar negeri. Hal ini tentu tidak terlepaskan dari kualifikasi dosen yang terus berupaya ditingkatkan agar dapat beradaptasi dengan tuntunan dan perkembangan zaman. Universitas Jember memiliki 4 kampus, yaitu Kampus 1 yang berada di Jember, Kampus 2 di Bondowoso, Kampus 3 di Lumajang, dan Kampus 4 di Pasuruan. Semua kampus telah memiliki gedung dan fasilitas pendukung yang memadai dengan total 1.935 unit dalam upaya meningkatkan potensi pendapatan. Universitas Jember merencanakan 9 divisi usaha yang akan dikembangkan yang terdiri dari divisi usaha berbasis bioteknologi, unit pelaksana teknis, kompetensi bidang ekonomi dan bisnis, kompetensi sumber daya manusia, layanan kesehatan, kompetensi bidang agribisnis dan agroindustri, kompetensi kepariwisataan, keteknikan, serta pertelevisian dan perfilman. Berdasarkan pendapatan dan kebutuhan yang telah dipetakan, Universitas Jember memproyeksikan pendapatan dan belanja dalam 5 tahun ke depan yang terus ditingkatkan dari tahun ke tahunnya. Keberadaan Universitas Jember yang mampu berbicara di tingkat internasional disertai dengan otonomi yang lebih besar diharapkan mampu menjadi faktor pendorong kemajuan Jawa Timur bagian timur di bidang pengembangan SDM pada khususnya dan Indonesia pada umumnya. Dengan kondisi yang demikian, maka Universitas Jember siap menjadi BLU, kampus merdeka dari Universitas Jember untuk Indonesia Jaya.
UNED siap BLU.
Universitas Jember berdiri pada 10 November 1964 di Kabupaten Jember, Provinsi Jawa Timur. Dengan mengemban cita-cita seperti yang tersemat dalam sesanti, Karyori Naras Ambuko Budi, Gapuro Mangesti Aruming Bawono.
Cita-cita tersebut dituangkan dalam visi misi Universitas Jember, yaitu unggul dalam pengembangan sains, teknologi, dan seni berwawasan lingkungan bisnis dan pertanian industrial. Universitas Jember saat ini telah memiliki 15 fakultas, 103 program studi, 1.260
Assalamualaikum warahmatullahi wabarakatuh. Hello, good morning ladies and gentlemen. Firstly, let me introduce myself. My name is Ika Oktavianawati. I will accompany you during this conference as the Master of Ceremony. It is great for us to welcoming you on the 3rd International Conference on Chemistry and Material Science, IC2MS. IC2MS is a regular conference which is held every 2 years by the consortium of the Department of Chemistry from Brawijaya University, University of Jember, and State University of Malang. And this year, Department of Chemistry, University of Jember has a role to organize the conference after it was postponed on last year since pandemic COVID-19 reason. So, it has been an amazing time for us to organize this conference this year. The theme of the conference is Innovation on Material Science for Sustainable Industrial Chemistry. This conference will be held in 2 days, on 12 and 13 of October 2021, and conducted fully by online Zoom meeting. Even though the conference is held by online, we believe that the conference will improve the academic atmosphere and open the opportunity for research collaboration among researchers, industrial practitioners, and the government. Well, ladies and gentlemen, as the first agenda in opening this conference, we will ask you to join us in listening and singing our national anthem, Indonesia Raya, together, and followed by the hymn of University of Jember. Okay, ladies and gentlemen, the second agenda is welcoming speech, which will be delivered firstly by Ibu Dr. A. Istri Ratna Dewi as the chairman of the third IC2MS 2021. For Ibu Dr. A. Istri Ratna Dewi, the time is yours.
Thank you, Moderator Bu Ika. Our honorable guests, ladies and gentlemen, good morning. In this great occasion, please allow me to deliver my report on the International Conference on Chemistry and Material Science opening ceremony. Before we start, it's really a great pleasure for me to welcome all of you to this ceremony, and for us, your coming and your support are highly appreciated. Your presence in this event indicates that we have some commitment to bring innovation, material science for sustainable industrial. We need to create and maintain the strong spirit to life sustainable industrial. We need to create and maintain the strong high challenge. Therefore, encouraging strong spirit and science must be done in many ways. The conference consists not only in chemistry area, organic, inorganic, physics, analytic, and biochemistry, but also in the material science such as molecular structure, functional material, material synthetic, and characterization. Even though the conference by online, we believe that the conference will improve the academic atmosphere and open the opportunity for research collaboration among researchers, industrial, and the government. Ladies and gentlemen, this morning we are here together to attend the third IC2MS, with it the most important moment of our course we have been fortunate to have. Professor Yong Chin Ling from Tsinghua University, Professor Byung Dak Park from Kyungpook National University, Republic of Korea, Professor David Lennon from University of Glasgow, UK, Professor Russell from University of Aberdeen, UK, Professor Manabu Abe from Hiroshima University, Japan, and Dr. Haslisa Bahruji from University Brunei Darussalam. And we have invited speaker, Zulfikar PhD from Universitas Jember, Anna Safitri, PhD from Department of Chemistry, Universitas Brawijaya, Dr. Irma Puspita Kusmaningrum, Department of Chemistry, Universitas Negeri Malang, and Nanang Masrujin, PhD, from Research Center for Chemistry, Indonesian Institute of Science. Next, we have received 150 scientific papers to best share and discuss coming from more than 7 universities and 10 different countries among 200 participants. Finally, I am very grateful to the Department of Chemistry, Faculty of Mathematics and Natural Science, Universitas Jember, Team Committee that's IC2MS, and the sponsor for their support to this conference. Last but not least, I wish everyone all the best in your work. Thank you.
Thank you, Bu Dewi. Well, the second welcoming speech will be delivered by Bapak Dr. Bambang Piloharto as a head of Department of Chemistry, University of Jember, and also as a host for the third IC2MS. For Bapak Dr. Bambang Piloharto, time is yours.
Thank you, moderator. I'm sorry. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. It is my great pleasure to welcome our distinguished guest, Vice Rector of Planning, Information and Public Relations Affairs, University of Jember, Dean of Faculty Mathematics and Natural Sciences, and keynote speakers, invited speakers, and participants of the International Conference of Chemistry and Material Sciences, IC2MS. IC2MS is annual conference held by a consortium of Department of Chemistry of 3 universities in East Java. Those are Brawijaya University, University of Jember, and State University of Malang. The recent conference is the event after the previous two events were held at Brawijaya University in 2017 and 2019. We are honored to have you all here and would like to thank you to your interest and participation in IC2MS. Our conference theme is Innovation of Material Science for Sustainable Industrial Chemistry. The conference covers not only in chemistry area, but also in material science, such as material synthesis and characterization, functional material, material computation, nanomaterial, and renewable energy. On the behalf of the consortium of the 3 universities, we hope that through this conference can get the opportunity to communicate and discuss chemical problem in research and stimulate collaboration among researcher, industry, and government. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Bapak Bambang Piluarto. And for the next welcoming speech will be delivered by Bapak Profesor Bambang Kuswandi as a Vice Rector of University of Jember, who will also officially open the conference for us. For Bapak Profesor Bambang Kuswandi, please welcome.
Thank you very much for the moderator to give me chance to give opening remark in this very interactive and exciting occasion. Assalamualaikum warahmatullahi wabarakatuh. Honorable Dean of Faculty of Mathematics and Natural Science, University of Jember, dear distinguished speakers, dear conference committee, especially the organizing committee, Ibu Dewi, dear participants and all who support this conference. Very good morning for all of you in this online conference of the 3rd International Conference on Chemistry and Material Science, IC2MS. First and foremost, I would like to express my deepest gratitude to Allah, the Almighty, for giving us time and chance for conducting this 3rd International Conference on Chemistry and Material Science, IC2MS 2021. It is a great privilege and pleasure for me to welcome all the IC2MS 2021 participants, and I wish to congratulate the Faculty of Mathematics and Natural Science, University of Jember, Organizing Committee, and the support for their effort and spending their time in putting this event together, the support for their effort and spending this event together in promoting chemistry and material science, in cultivating an exciting interdisciplinary approach in this field as one of the State University in Indonesia. University of Jember tries to implement an active approach in finding ways to improve imaginative work that contribute toward the advancement of the country throughout a significant expansion of time. Despite the COVID-19 pandemic that has hit the whole world, where any country, including Indonesia, has felt the effect of this pandemic, despite this dire circumstance, we are exceptionally pleased to see Department of Chemistry, Faculty of Mathematics and Natural Science, in collaboration with other consortium, University of Brawijaya Malang and University of Malang, who has shown tireless commitment in continuing our mission to promote University of Jember at the international level, particularly as evident through the conducting of this conference. We are confident that this conference will be a virtual meeting platform for chemists and material science researchers to share and exchange breakthrough ideas with one another, with thusly prompting productive thinking and making successful joint effort and collaboration later on. The field of chemistry and material science, including their branches, are in line with our strategic plan to develop University of Jember as center of excellence and research and innovation internationally, especially in agriculture, biotechnology, industrial agriculture, and health sciences, even in the era of the COVID-19 pandemic that hit the world. Certainly, we believe that IC2MS 2021, with its international participant level, will contribute to making University of Jember on par with any reputable university internationally. To all the keynote and invited speaker and all participants, we sincerely hope that this conference will serve as a platform to create and strengthen collaborative ties internationally and locally. Finally, it is my favorite hope that the scientific discussion will be mutually beneficial to all, and I wish all participants to have a wonderful conference in this IC2MS 2021. And without further ado, with recited Bismillahirrahmanirrahim, I open this conference officially. Thank you very much for your joining in this conference. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Bapak Profesor Bambang Kuswandi, for opening our conference. Well, ladies and gentlemen, that was our second agenda, the main opening ceremony of this conference. And for the next agenda, we will have to start our general lectures, which will be conducted by our honorable keynote speakers. But before that, to make our hearts are peaceful and being blessed by God, it would be great if we start this conference by praying in accordance with our own beliefs. And I would like to lead this praying by saying Basmalah, Bismillahirrahmanirrahim. Okay, ladies and gentlemen, now before we move on to the next session, we would like to invite you all to have a picture together. So for all the audience, please on your camera so we can take your best picture for documentation. And for the committee, please give your hand on taking our picture now. Are you ready? Okay, I will start it by counting. Well, okay, thank you so much for the audience for your participation. Honorable keynote speakers, Professor Yong Chien Ling from Tsinghua University, okay. Committee, maybe I will finish my statement first. Okay, I'm sorry for this inconvenience. For the first speakers, keynote speakers, Professor Yong Chien Ling from Tsinghua University, and then followed by Professor Byung Dae Park from Kyungpook National University, and also Dr. Hasliza Bahruji from University of Brunei Darussalam. This general lecture will be moderated by our senior lecturer on Department of Chemistry, University of Jember, Bapak Zulfikar PhD. And for our moderator, Bapak Zulfikar PhD, the floor is yours.
Good morning. Warm welcome to you all in the third International Conference on Chemistry and Material Science. We have an interesting theme for this conference, Innovation on Material Science for Sustainable Industrial Chemistry. First of all, let me introduce myself. My name is Zulfikar, as a lecturer at Department of Chemistry, Faculty of Math and Natural Science, University of Jember, and I will be moderating the plenary session today. It's a great pleasure for me to introduce our keynote speaker today, who is going to talk to us about their expertise area. Professor Yong Chin Ling from Tsinghua University, Professor Byung Dai Pak from Kyung Puk National University, and Dr. Hasliza Bahruji from University of Brunei Darussalam. We would like to let you know that each keynote speaker have 40 minutes for their presentation and 20 minutes for the question. If you have any question, please use the chat feature in this Zoom webinar. Now, let's welcome Professor Yung Chulin, who would like to discuss retrospective of dioxin-like compound monitoring in Taiwan environment and food. The time is yours, Prof. Thank you.
Thank you, Mr. Chairman. I shall open my slide. Could you see my slide? Couldn't see my slide. Yeah, so to see that. Oh. It's just my slide. Okay. Thank you, Mr. Chairman. I'm Yong Chin Ling from the Department of Chemistry, National Tsinghua University. First of all, I would like the committee to invite me and give me this opportunity to introduce about dioxin-like compound monitoring in Taiwan environment and the food. I would start my talk with a brief introduction and followed by 4 research projects we have carried out for the past several years. Could you see the PPT file? Yeah. To the first screen.
No.
My lab is green analytical chemistry, working on green and analytical chemistry, and we use a lot of different mass spectrometer, mostly in the environmental, food, and the material science. No, previous one. Previous one. Can you take this away? Okay, the compound I'm talking about this morning is the persistent organic compound, POPs. And it is regulated by the International Treaty in year 2004 in the Stockholm Convention. And the subject is the dioxin-like compound, abbreviated DOCS. It including 135 polychlorinated dibenzyl dioxin and the 75 polychlorinated dibenzyl furan and the 2 online polychlorinated biphenyl. And what we are interested in is about 29 total, what we call the dioxin-like compound. Those are the most toxic one. The major source of this dioxin and the PCB, they are produced unintentional as the byproduct due to incomplete combustion, and also chemical process involve the chlorine, and also some natural process like the forest fire and the volcanic eruption. And it is found throughout the environment and will eventually go into the human body through the food chain and be magnified. So the first subject will be on the e-waste recycling. And this is a very interesting paper on the front page of the ESNT in year 2012. And it mentioned the electronic waste or the trash or inorganic trash are transported to the North America, to the China, through the Hong Kong. And it was disassembled and the process, and then finally it was spun out to recover some precious metal, etc. And what you could see on the bottom right is the ash of the burning waste after the process, and it's piled up in the river on the city called Guiyi. And that is year 2012. But in Taiwan, we have this experience back to the year 1960. On the top left is the photo of the people working there at night time, and you could see them working in front of their home, etc. And on the top right, you could see they are burning this dismantled electronic waste by the riverside called the Allen River. And at the bottom left, in year 1983, the government has installed an industrial park to process this. But nevertheless, the recovery of the precious metal, for example, the gold from this electronic waste is very, very active. Until year 1993, the government has forbidden the import of the waste to Taiwan. And what you see on the bottom right is the waste piled up by Aaron River. And it is until this year, the government has started to do the remediation, but only on the river bank. So this is the experience we have in Taiwan. So this is the project we have carried out in early regarding the study of this dioxin-like compound in the fish and the ediment in the river, Aaron River. And in this slide, you could see on the top left is the Taiwan Strait. And on the middle is the river called the Aaron River. And the city is called Wanli. It means bay, because this is the bay for the river to flow into the Taiwan Strait. And there are many activities, especially on the left. You could see the baying side. That's where we found the highest dioxin-like compound in the sediment sample 4 and 5. That's close to the riverside of the burning site. And what we found, dioxin, the TEQ range from 14 to 14,200 picogram per gram TEQ. And the difference is about 100 times. And for the PCB, it is from 9 to 1030 picogram per gram TEQ. And the difference is about 100 times. So this is for the sediment. And if we take the lowest value as the background value, you could see this contaminant concentration has magnified 1,100 times respectively for the dioxin and the PCB. And for the fish, the highest is not surprising, are found at the exit or at the junction of the Aaron River and the Taiwan Strait. Among the 8 fish, the 3 highest ones are all sampled in this area. And for the dioxin, it is TEQ concentration range from 37 to 2,084 picogram per gram TEQ. That's about 60 times difference. And for the PCB, it is less. It is about 10 times difference from 12 to 120 picogram per gram TEQ. So what this means is that this Aaron River and also the fish caught in this river is heavily contaminated. This is back to year, I think, 1993 or 1994. Next one. So in brief, in this paper we published in year 1995, we have pointed out the sediment sample and also the fish sample, the dioxin and the coplanar PCB, they are all very high compared to the background value. And we also try to identify the possible source. For example, for the dioxin, in my phone, there are some discharge PCB in some electrical capacitor left there before. And mostly it is due to the open air incineration of the U-waste. And there may be some pentachlorophenol from the nearby chemical industrial manufacturing plant. And we also do an estimation of the risk by calculating the daily intake value. And it is range from 28 to 450 TEQ picogram per kilogram weight per day. And just by only consuming the fish caught from the Aaron River, and this is very, very high, then the daily intake value, tolerant daily intake value suggested by the World Health Organization. So with this, the first reported and the very striking data, this research work has been published or have been announced in the United Daily News in the year 1995, and it's on the front page news. And to my personal understanding, this is probably the first environmental report news was put into the front page on the largest newspaper in Taiwan at that time. And the title of this news is that scholar take sample and detect poison of the century poison and the Pcb. And these are far exceed the international food standard. And they also warn that the poison fish will harm humans and should not be ignored. And also, we also suggest the government to establish a standard for dioxin and for risk assessment. And the next subject I would like to go into is the municipal solid waste to energy, abbreviated WTE, incinerator in Taiwan. And this will go back about 25 years ago, because in Taiwan, the land is very limited. And also the population is highly dense. So there are not many open space to deal with these municipal solid waste by traditional sanitation approach. So the government has decided to use the incinerator. And the incinerator will burn the waste to energy. So this will be just to get rid of all this solid waste, because what you left with just the less amount of the ash. So from that policy, about 20 years ago, Taiwan has built around 23 or 24 municipal solid waste incinerator, MSWI, throughout the Taiwan Island, from the north to the south. It is planned there should be at least one incinerator per county or per city. And what you see on the right-hand side is the Hsinchu incinerator. So the second project will focus on our long-term monitoring of the ambient air and the soil and also the stack gas from this incinerator. And before that, I would like to introduce the dioxin control and the emission standard in Taiwan. Because about 25 years ago, the government had made this policy. So have started to work out, so to formulate various standards. And this is probably as stringent as what we have in the world and nowadays. The first is for the waste incinerator. And the dioxin control and the emission standard is 0.1 nanogram TEQ per normal cubic meter. And for small and the medium size, the smaller value is for the newly built one. It is also the 0.1. And for the steel industry electric smelting furnace, it is 0.5. Next. So this is the problem will be met, I think, global-wise when you plan to build a municipal solid waste incinerator in a location. The public's perception on the construction and the operation of the to-be-built neighboring incinerator is simply said, not in my backyard. Limbai. And the reason, there are many. But in Taiwan, that is the public believed by the construction of the municipal solid waste through the operation under the daily entry and the exit of a large number of garbage trucks will eventually increase the local environmental and the safety of the resident, although the government has provided feedback measures. I think this is the first time the government has this kind of policy. But the local residence is still feel insufficient. So before the initial operation of this incinerator in Hsinchu, we have worked together with the local Environmental Protection Bureau and to do a monitoring. And what you see on this slide is the monitoring value each year from year 2000 to year 2015. And on top is the stacked gas. In the middle is the ambient air. And in the bottom is the soil. And what I should point out is that in the bottom for the stacked gas, the highest is 0.1. That is the standard. So you could see for all this year, the stacked gas always below the emission standard of 0.1. And in the middle is for the ambient air. And for the ambient air, in Taiwan, we don't have this standard. But for this, if we use those from the Japanese, will be a single digit value. So here we'll see it is also very low in the ambient. And in the bottom is the soil. And you could see these are all single digit value. But in Taiwan, we have a loose standard. It is 1,000. So all these, they are under the emission or the regulatory standard. And this project was carried out continuous by our university, by my laboratory. And all these report, the yearly report will be reviewed by the supervising committee, and all the result will be posted on the local Environmental Protection Bureau web. Next. So at the very first beginning, what we do is to set the very comprehensive monitoring plan as shown in this slide. At the top left, you could see a star. That's where the incinerator is located. And then the smaller circle, it is 2.5 kilometer center around the incinerator. And the next one is 5.0 kilometer. Under the various location, A, B, C, D through the K, they are in the school or in the residential area, because these are the two sensitive areas we are more considered. So we have carried out this modeling at the Triburn and after the fully operational in year 2000 and 2001. And that is for the ambient air sampling. The procedure we use is follow the US EPA standard procedure for sampling and analysis. And usually, this sampler will located on the top here is the elementary school building in the top floor. And on the right is the sampler. And you could see after the sampler, the paper will change from white to gray. And they usually will take a 48 hours of sampling period. Then we'll bring to the lab for analysis. And in this case, we are using the high resolution mass spectrometry. And what I would like to emphasize is that the quality control is very important in this case. So after we get these initial results, one way to convince the local resident that these major values are okay, usually we just will compare to the other reported value in Taiwan incinerator. And on the left four is what we got in this research. And in three times, they are all lower or similar to Taiwan other incinerator, but in the first one, that's in the February of year 2000, it is higher, and but still lower than the next neighboring one. And for that, we'll explain the reason later. So this is one way we used to convince the local resident. And the other goal we are interested in to see where the source of this dioxin source come from. So we put all the major results from the ambient, soil, and the state gas all together to do the principal component analysis. And you could see they could divide it into 6 different groups. Maybe they have 6 different sources or environmental effect, etc. And it is not clear to see from here. Next one. But if we use the hierarchical tree plot of the cluster analysis, you could see it is more clear. From the top left, you could see A. The first character A stands for the ambient air. So the ambient air, they are all the same, all very similar. But when you go to the middle and the below, you could see S1 and the S2. Those two are soil. Those two are soil. So we could say that the ambient air, they have similar dioxin composition. And you could also see on the rightmost ditch, right, 1 and 2. 1 means in summer, 2 means in winter. So in summer and the winter, they will be different. And although the environmental condition is all the same, and this is because in the weathering condition is different. Next one. Okay, so the first project, I think probably what we could see is that we have made clear that the incinerator does contribute dioxin to the neighboring area. And we also have introduced the technology to our friend, and this is the one course or the workshop we have carried out in year 210. And the participants are from the southeastern country, and the 4 are from Indonesia. Next one. And among the course we have introduced is the dioxin monitoring. And on top of this, we have invited these students to go to the National Institute of Environmental Analysis to see how the dioxin is being analyzed. And on the bottom, we have introduced them as a Pcb sampler, so they could do the sampling back to their hometown and send a sample to us for analysis. And for these PS, you could sample maybe up to from 2 to 4 weeks. So the result will more represented. Next one. And this is outcome of this international monitoring effort. And what you could see at the bottom left, there are 2 sampling sites from Indonesia. And I think maybe it is due to the effort of the 2 faculty members from the Islamic University of Indonesia. And they have set the sampling site there. And you could see that their values are all very close, except one in Malaysia. But all they are lower than the background value in Taiwan. And this is not surprise. Taiwan is industrially in many areas. Next one. And we also do the cluster analysis is just to see where does this dioxin come from. And it is a little bit from the Taiwan. You see that the first one is the industrial wood composter or the wood combustion. And the second one is the unleaded gasoline fuel, and the third and the fourth is from the diesel truck. But the fifth one is the pentachlorophenol. And I think maybe is there something to do with the wood industry in this country? Next one. So that's what we have do with the dioxin. And in the recent year, we are also trying to monitor the PM 2.5. And what we use the homemade monitor, PM 2.5 monitor. And this could simultaneously determine the concentration and send it as well as the concentration, location, and the time back to the lab computer and so on. So what we use this to do the spot monitoring on the mobile inspection. The spot monitoring is to monitor the PM 2.5 inside the incinerator. And the mobile inspection is just to monitor the PM 2.5 in the perimeter of this incinerator in the same time. Next one. And before we do this monitoring, we have to do the zeroing and the calibration. We do the initial calibration in the laboratory. Then we bring this to a nearby air quality station in the Hsinchu Science Park Air Quality Monitoring Network, and to do a 3-hour zero and the calibration. And the shown on the right is the zero, and the bottom is the calibration. And by this, we feel more comfortable that the PM 2.5 value we got will be comparable to those obtained by the air quality monitoring station PM 2.5 value. Next one. So this is just the example. On the left is the spot monitoring in the bottom edge storage pit, and on the bottom is just the corridor next to the elevator. And you could see during the 3-hour monitoring, there are some sharp rise, but this is not due to the incineration. This is not due to the incineration. And also in the right, because this is the monitoring device could also monitor the PM1 and the PM10. So we have to do the ratio of the PM 2.5 to PM10 and the PM10, PM1 to PM10. And we could see at the bottom right, there is the abnormal value. And this is the area next to the elevator. And this is because there are PM10 too many, and they are fall down on the floor due to the flipping or the sweeping dust. So it is not the PM 2.5 is too high, but it's due probably due to the PM10 has been due to the sweeping operation, and the dust has fall down on the floor. And again, we have also do the mobile inspection, and the result is shown on the bottom. And there are two routes. They are on the reverse direction. And this value, they are all green, means they are all low in the normal value. The low in the top, what we have shown in the bottom edge storage area, there are some sharp rise, but nevertheless, they will affect the neighboring areas ambient air quality. So I think in this project, what we have come to is that the issue of local environmental and the safety of the resident from the Hsinchu incinerator is not an issue of the government, because we have continuous do the monitoring and put the data open in the website. Next one. Okay, then the third one is regarding the food. And this has something to do with the rice oil disease, and this has been reported or has been occurred in year 1960 in Japan. And in Taiwan, it occurred in year 1979, and we cannot find out the cause in the year. Finally, after we send it out to the scientists in Japan, and they have do the analysis and found out it is the PCB that has poisoned the rice oil. But in Taiwan, I think the number of victims and the damage is less compared to those in Japan. But what we have found, because of continuous medical examination of the second and third generation of the victims' children, and found out they had a noticeable development disability. So this is the case. The environmental contamination, the risk will be affect your next generation and the third generation children. Next one. So what we do is that we just use the IC2MS and use the isotope dilution. And the first thing is that what we like to see where this PCB comes from. And in Taiwan, that time the PCB might come from imported from the Japan, as the KC400 and the KC500 brand name, and also from other clone from the United States. And previously report saying they are coming from the KC500, but after a comparison of these, the PCB pattern, the top one is from the rice oil. And compared to the BCD, the three different brand name PCB, it is appear it's more like coming from a mixture of KC400 and the KC500 and at the bottom. So with this, we have clarified where the PCB comes from. Next one. And we also do the dioxin analysis and the PCB analysis. And for the dioxin analysis, has never been done because in Taiwan at that time, what we send to Japan is just for the PCB analysis. And what they have done is the copolymer or the toxic PCB analysis. Next one. But since we have done the dioxin and the copolymer PCB, so we could calculate the TEQ, the toxicity equivalent quantity. And what we have found out, the toxicity coming from the PCB is only 35%. The other 2/3 come from the dioxin. And that is because during the heating, this PCB will be reaction and to form the dioxin. So I think what we could say is that the toxicity was underestimated previously. Next one. The third one or the last one is the total diary study. Next one. And the analytical method, we use the standard, and it's a combination of the US EPA and the US FDA and the LAC standard method. And this standard is developed by our laboratory, and the ETO developed according to ISO 17025. Next one. So this is the quality control, the lipid content, and the method brand, and also internal standard during the 3 hours, they are all within the control limit. Next one. And we also do the measurement uncertainty during the initial method development. And what we see is that the most effect is due to the precision. That's the instrumental analysis. Next one. Because the concentration is very low. In this case, PPB to PPT. And we have also participated in the interlaboratory comparison in year 2004. And the sample are chicken sample and the trout sample, and you could see there are some red spots in the middle, and those are the result from our laboratory. So it is all within the acceptable range. Next one. And that is for PCB. Again, it is all very good within the range. Next one. So after the 3 years and a very expensive budget, what we have come out with is the concentration label. And on the top is based on liquid weight, and on the bottom is on the fresh weight, because for regular standard will based on different weight. For fish, it will be on fresh. For all the others, will be based on liquid. And all we could see, the lower is the pork, and the highest is probably in the fish. Next one. And for the fish, the highest is probably some expensive and the more fatty, the catfish or salmon, etc., or the eel. Next one. And we are also very interested to see that there are some sample, their value will vary by season, especially for the milk. It is higher, it is lower in winter, or higher in summer. And this is because in summer, the milk price is high, so there will be better fit with the imported grass. But in the winter, they will fit for the domestic grass. So that makes the difference. Next one. And we don't have the regulatory standard lifetime, so we compare the EU maximum limit. And some will over. Some will over for only year 2000 to year 2004. But at least during the project period, year 2000 to year 2003, it is show a decreasing trend. Next one for the milk. And the most interesting is what is the direct exposure to the dioxin-like compound. And we use this formula to do the calculation. And for the average daily intake is about 1.62 for male. And for male is about 1.23. And the WHO recommend is 4. Is a 4. And the country has a depth 2, but at least in Taiwan is all below 2 at that time. Next one. So for this result, I think probably what we could say is that the ADI we got after the 3-year project has shown the citizen that their intake value is below the WHO, at least the average. But we don't have a regulation to control the PCDF. Next one. So this is probably the last one. My talk is that this is the in year 2006. Right? The government has issued a specification for the handling of dioxin and dioxin PCB in food. And it is in Chinese, but it is very similar in the EU. It is including the meat, the milk dairy product, the egg, the fishery product, and also the oil. But in year 2013, the government also included the food for infant and child under 3 years. And you could see the number, the 0.1 or 0.2. It is almost 10 times lower than those for the adult. So I think this is what we should pay more attention to, is that because for the infant and the children, they are more vulnerable to this dioxin contamination and risk. Next one. So with these 4 projects, we have carried out 2 in environment, 2 in food, all based on the parts of the dioxin. And what I would like to say is that as the professional, we have our research, and our research report sometimes will become the basis for government's necessary reference. And our research data and the analysis result will attract not only the government attention, but eventually it will influence the policy formulation in the long term. Next. So I think our continuously contribution of our academic expertise to the food and environment related work is very needed. And that is what the experience I would like to share with you. Thank you.
Thank you very much for your presentation. Very nice, Prof. It is the time that's for us, for participants, have a question session. Please again, type your question in chat feature and submit it to us. The first question, Professor Chunlin, came from Mr. Halim. Mr. Halim, according to your experience, hang on. Yes. What is the most difficult part or need to give attention when using MS to detect a compound in the air or atmosphere? What is the next application of MS that haven't applied yet, but it will become a breakthrough? Thank you.
That's a very good question. I think the first answer is that it is expensive because it's a high resolution mass spectrometer, and also you have to be well maintained because you are doing the trace analysis in the pico and the femtogram, and this is the same in the air. So you have to dedicate instrumentation for this, and the very expertise person to operate the instrumentation. And the next application mass spectrometer have been applied yet. It will become, so if you're, I'm not sure about your question is for the application of the mass to environmental and the food analysis or other field or the material science.
I saw this maybe in the air, in other area. I'm not sure.
Okay. Yeah. Okay. We'll say in the air. I think in the air, again, you could see that for this dioxin, we have to do a sampling a very long time, and then maybe right now we'll take 3 to 5 days to do the analysis. But right now there are some pollutants. They maybe have a short life and unstable. And also what you would like to do is to monitoring their manufacturing process. So a portable mass spectrometer with high sensitivity and that could interface to the good separation GCMS, I think it will be needed. And we have also trying to exercise that in Taiwan.
Okay. For the next question, that's Mr. Agung from our university. According to your experience, how about the microplastic pollutant? Is that as a source of dioxin or have similar effect? And then are there any correlation between 2.5 between PM 2.5 of dioxin, maybe 2.5 PM, I don't know, that's dioxin in content in the air.
Okay, those are very good questions. I think for the microplastic pollutant, it is the international concern. And in our group, we are also doing that. But we do not relate it to the dioxin. But because the microplastic pollutant, when it is in the ocean, they will only be degraded, but they are not burning. But once they have been collected or pushed in the seashore side, usually they will subject to the burning. And when you burn the plastic, dioxin is the natural pollutant. So yes, it will be a source of the dioxin in the follow-up treatment of this microplastic pollutant. And on the second one is that any correlation between the particular matter 2.5 micrometer in size and the dioxin content in there. That is a very good question and a very difficult to answer. Actually, when we do the dioxin sampling, we have collect both the gaseous dioxin through absorbance, and also solid or particulate dioxin through a filter paper. And we have tried to do the correlation of the dioxin content with the particulate matter we collect, and also just the gaseous dioxin. And the correlation is not that good. It's not that good. And maybe, and it also vary on the location of the sample where you collect. But we are sure is that these dioxin, they will probably, most of them will be in I think in both the solid phase or in the gaseous phase, because when we do the state gas sampling, what we will see, the dioxin will appear in both the solid phase and also in the gaseous phase. But with the particulate matter 2.5, we don't have that data yet, because they are not much PM 2.5 fine particle to be collected. And you want to do such a low amount of dioxin determination, you have to collect a lot of the PM 2.5. So we don't have that data yet.
I thought there is any time for one question. That came from Irianti Nata, Chemical Engineering, University of Lambung Mangkurat. The question is, based on your research for all parameters contaminant, which have been detected, and what is the next step to overcome those problems?
Well, thank you for this question, because that the research we are carrying on now. As you could see from my presentation, the analytic chemistry in my group, we just used to find the problem and to understand the problem. And we will advise and ask the government maybe to set a policy and the better way to have the standard. So by this, when it is under the regulatory control, I think the problem will become less of concern. But for this is the end, the management by the regulatory process. But another way is from the source. It is from the manufacturer or at the end by the consumer. So we have done maybe a lot of the green chemistry related work to develop the green chemistry process and to advise the manufacturer to adapt to the green chemistry manufacturing process, and also ask the consumer to think of the green chemistry and to buy green product, green consumer product. So by this way, we could work together from the source and from the end to reduce this pollution problem. Thank you.
Okay, the last question, I thought that came from our Vice Rector. The question is, since we are facing this analytical 4.0 era, what was the role that will change in environmental chemistry, like the use of IoT and cloud in environmental analysis?
Okay, I think we have touched this subject a little bit during my PM 2.5 monitoring. We have designed and manufactured a monitor device by ourselves and then set up the cloud and to do the real-time monitoring and the real-time transfer of the data back to the computer in the laboratory. But after a while, we spend a lot of time to do the data analysis. So I think this is probably the environmental chemistry will meet the desired. We need to get more data in the most short time period, and to get the result as soon as possible. And all these will require the IoT and the cloud technique. And so the data analysis or the software or the statistics analysis, I think this will all become important because we have to face a lot of data in the near future.
Okay. Thank you for the presentation, Prof. Young, and let me give a big applause for him.
Thank you.
Now that's really tight schedule. So next keynote speaker, Professor Byung Daeng Park, will share his experience and delivering the topic of nanocellulose-based functional composite material for detecting pH or color change. But let me introduce the CV or curriculum vitae of Professor Park. He got bachelor from Chonan National University in Korea and master in chemical engineering, University of Toronto, and he got also received his PhD in wood science from Laval University of Canada. Professor Park worked as scientist in Foreign Tech Canada Corp from 1999 to 2000, and a research scientist in Korea Forest Research Institute from 2002 to 2006. He joined the Kyungpook University in 2006 as an assistant professor and was appointed a professor in the Department of Wood and Paper Science in the same organization. He got so many awards from because of his leading position, visiting position, and significant membership in organization as well. He also editor board and consultant in many companies. Finally, he also published so many papers. I couldn't read it all, and the time is yours, Professor Byung Daeng Park.
Thank you very much for the kind introduction. Can you hear me?
Yep.
Okay, so let me try to share the screen first. So can you see my screen?
Yep.
Okay, thank you. Thank you very much for the give me the chance for this wonderful conference, which is a third international conference on chemistry and the material science. Particularly, I'd like to thank you for the Professor Bambang Piluhatro, who had been in my lab about 5 years ago, maybe. And then I know him, I guess he's on the audience today as well. So what I'm going to do today is I'm going to talk about the nanocellulose-based functional materials for the detecting pH or color changes. So mainly what I'm going to do is I'm going to use this nanocellulose and then make something functional material to detect the color change depending on pH. First of all, I'd like to appreciate some of the contributors to my work. Dr. Mi Jung-jo, she did her master with me, and she did PhD in the University of British Columbia in Vancouver, in Canada, and she is now the postdoc fellow in the Aalto University. She also contributed this, and also Dr. Nanang Masruchin. He did his PhD with me about 5 years ago, and he is a research scientist, the research center for the chemistry at LIPI and the Bogor, Indonesia. And I also appreciate Dr. Hussein Kanjanjada. He is in my group now. He is a research professor at the same university. And Dr. Hamid Reza Pirareshi, also he is a research professor in my group. And also I'd like to appreciate Dr. Valerio Cusin. He is a professor at the Department of Chemical Science, University of Padova in Italy. all of these people that contributed to my presentation work. So let me give the outline of my presentation. First, I'm going to talk about the interaction. As you know, it's a nanocellulose CNF, CNCs are being used, the photonics, the composite, the medicines, the modification, films, and forms. And as you see, the production of the nanocellulose increases pretty much over the time, which is much more than carbon nanotubes, but a little less than the carbon nanofibers, but still nanocellulose production is still increasing. And also it is expected about in 2024, it's a production going to $1 billion market in the US. And then I'm going to talk a little bit the nanocellulose, what kind of nanocellulose I'm talking about. And then I'm going to talk about the cellulose nanofibrillary bromo-cursor green composite, which is used for the detecting color changes depending on the pH. And also CNC bromo-cursor purple, cellulose assay film indicators, cellulose nanofibrillary neutral red, PVA film as indicators, and then talk about CNF-based hydrogels, which also used for the detecting color changes. And then come the conclusions. You know, the nanocellulose are being used in many different applications, including the photonics and the electrostatics, some medicals, some surfactant, those kind of things. But today, I mainly focus on the smart composite materials or hydrogels, mainly used as kind of functional materials, making a good applications. You know, there are some different ways of the isolating nanocellulose from wood or some other lignocellulose materials. First thing is you can use the acid, sulfuric acid or hydrochloric acid, even phosphorus acid to remove the non-cellulose materials and to get the nanocellulose such like this. This is called, we say, cellulose nanocrystals. But also you can use mechanical grinding or shearing like this, and you can have the microfibrillary cellulose. Some of them cellulose contains in nano sizes, but mainly the mix of the micro and the nano sizes as well. And recently in my lab, we use the ammonium persulfate oxidation, I would say APS oxidation, using the recycled MDF fibers. We use the MDF panels and isolate the recovered fiber, recycled fibers, and then we use the ammonium persulfate oxidation to get the nanocellulose crystals, the CNC. In this case, you don't care about the lignins, the hemicellulose present in the recycled MDF. We just get the nanocellulose crystals from recycled MDF fibers. You know, and you have the different types of methods and to isolate cellulose. When you have this kind of cellulose nanocrystal, you can get using the sulfuric acid, diluted about 64%. And then you have this kind of whiskers. They have very pointed end, a little bit thick at the middle, and the diameter is about 7 nanometers, the length of 175 nanometers. This is a red analysis. The mean means the length and diameter together about the 700 nanometer. When you have a temp oxidation, we can get the cellulose nanofibrillary like this, which is diameter is about 5 nanometers, and I didn't measure the length of the nanofibrils. And when you do wet analysis, it's about 314 nanometers, including length and width. But from based on the Professor Iswai's result, the length of the CNF is about 1 microns. When you have the APS oxidation, we also have the CNC, which is like a whiskers. And this kind of the size distribution is about 221 nanometers length. You know, why we are so much interested in nanocellulose? You know, the nanocellulose from wood is renewable, biocompatible, and biodegradable, and also they have exceptional mechanical properties, and also we can change their surface to make it compatible with the polymers and some other materials as well. For example, here, the nanocellulose crystal is about the very high tensile strength and the modulus, which is about 7.5 gigapascals, 145 gigapascals as modulus That's exceptional. It's better than glass fibers. That's why many people are interested in this nanocellulose. So, for example, this is kind of a small experiment making the nano composite using the cellulose nanofibril, which is from temp oxidized cellulose, the oxidation, and the cellulose nanoviscose, which is prepared by sulfuric acid. And then we use the different molecular weight of the PBA, 22,000, 60,000. And then we added the different level of the nanocellulose in the matrix, which is a PBA. And then we got the tensile modulus and tensile strength. As you see here, 1% of the CNF, the raw molecular weight PBA 22,000. That's excellent, the tensile modulus. It's much better than the others. So when you more than that, about 3%, over 3%, it's actually decreasing. But the tensile strength is better for the CNF of the 60,000 molecular PBA, but it also decreases above 3%. This example shows the CNF or nanocell has excellent mechanical properties. So what I'm going to do about this, the functional materials for the Technicolor, the idea is very simple. We use the nanocellulose, we're going to combine the nanocellulose with pH indicator together, and then use for the detecting color changes. Why? Because nanocellulose is hydrophilic, and also this is non-soluble carrier. That what I'm saying is that when you mix with some other materials, and nanocellulose is crystallized, they are not dissolving any kind of the water soluble or polymers. So we're going to try to different types of the nanocellulose here. We use the CNF, which is prepared by temp oxidation, and also we use the CNC, APS, and also some of the MMPC. And then we use the different pH indicators like a bromocrystal green. They are changing colors below the pH 3.8, it becomes yellow, red. They change the pH above 5.4. It's a green or blue. This usually it's green, but it's when you use tab, it changes green as well. And also we use the bromocrystal purple. They change the colors to yellow below the pH 5.2, about the blue purple above pH 6.8. And also we use the neutral red, which change colors depending on the pH like this. So what I'm going to, the idea is that we're going to have this kind of the film indicator, put them in the storage in the fruit or food, some of things. And then when your time goes by, and then the pH or something in pH changes because of the carbon dioxide or some other acid release, those kind of things. That's the idea. So combining nanocells with pH meter, pH indicator together to making a composite materials to as a functional materials to making the pH color detecting materials. So first we worked on the cellulose nanofiber, which is prepared by temp oxidation with the bromocrystal green like this kind of things. But it's not able to use it as it is BCG because there's not much reactive site here. And then we activated BCG using ethylamine and the cyanuric acid in acetone, and then make the sulfonic chloride groups on here. They are changing the color because of the protonation, deprotonation, those kinds of acid base like this. So, and then CNF, and then we also need to change surface of CNF because to make the compatible with the BCG together. So this is a temp oxidized CNF. They have the top sodium carboxylate on the surface, which is negative charge, and then we use EDC, NHS, and proper reaction conditions, and then we have the intermediate product, and then this intermediate product reacted with activated BCG, make the BCG conjugated CNF like this. And then we also tried amination. It the same, the nanocellular fibrils, and then use the epicohydrin, and then make the some kind of the reactions, and then provide the amino groups on the surface. And then we make a reaction with aminated CNF with activate the BC to make this kind of the conjugated product. So, and then we checked whether there is a reaction is properly done or not. And this is esterified with CNF and the control. The intermediate product, this is CNF with the BCG. One is the CNF with the esterified CNF. And then this kind of product. And then we have the new peaks for here, the composition of CNF and the BCG composition here and here. These are the new product. That means that these CNF and surface modified CNF has been reacted with the BCG, activated BCG, and also aminated with new peaks for the CNF BCG, which is aminated the CNF, and then there's new peaks. That means also there's a reacted amino groups, reacted sulfonyl group of the activated the BCG. And also with the TGA and a little bit changed, esterified, and the degradation temperature increased, and also degradation temperature increased, either esterified CNF or aminated CNF. That means also indicated the activated BCG has been reacted on the surface modified CNF. And then we also changed we check the color, any color changes like this. Esterified CNF is the BCG1, CNF1, and CNF2 like this. And then esterified CNF has a good color change. The above pH 5 is all green. At the below pH 2 is yellow like this. We have films and put them in the deep purple solid pH 10 and the pH 2. They change different colors like this. Then it was good. But aminated one is not much good. There's not much the distinctive color changes. And then we just discard this option. We use esterified the method for the further modification or further research. And also this is unpublished data, but we prepared the films and then put them in the different pH 2 and the pH 10 solutions, and then I keep them in the up to 32 hours. They change the colors like this, and the film and the purple solution. Same as the other one is in previous research, we just put it in the purple solution particles, but we prepare the film in acetate, cellulose acetate, and then they change the colors in 32 hours. I actually changed about 27 hours. And then I put it, just curious, and put them in this film in the milk, and then keep it about a month. I mean, milk is spoiled. I mean, it's gone bad. And then they change the colors, like change the colors. The control is nothing changed, and they change the colors to the yellows because of the milk has produced a lot of the lactic acid. And then we try to use the CNC, which is prepared by ammonium persulfate oxidation, and also combined with the bromocursor purple in cellulose acetate film as a kind of film indicators. As you see here, you have the bromocursor purple like this. We need to try to activate this sulfide groups, and using the same method as previous. 3-methylamine, cyanuric acid, and acetone, and we also sulfonic chloride BCP here. As you see, the bromocursor purple change colors below 5.2. pH 5.2 is yellow. Above pH 6.8, it becomes purple. So, and then we have this APS oxidation also provides a sodium carboxylate group here. Actually, you have a carboxyl group, you add the sodium hydroxide here, and then sodium carboxylate group here. And then we use this kind of EDC, NHS, and the same as the previous, the bromocursor green, added the byproduct, and then we provide this, and then make a reaction this with activated the bromocursor purple, and then we made the bromocursor conjugated CNF like this. And then we checked it whether there is any chemical reactions between them. We did using FTIR, and we have this kind of reactions and the specters. We have carboxylated CNC. This E means esterified CNC activated BCP. This is kind of composite materials. And then we have a new peaks, these kind of peaks. they are responsible for the new reaction, the reaction between acidified CNC and activated bromocursor purple. Also, there's some the specters, the shift and the composite materials. These indicate that there is a chemical reaction between them. And also we did XPX X-ray photoelectrospectroscopy to see any changes in the surface in chemistry. As you see here, the CCNC, the carboxylic CNC, this is C and the S, the sodium and the oxygens and nitrogen, those kind of things. And the acidified CNC, we have still the chloride, it's a little bit chloride because we use the EDC. And also we have a carbon and nitrogen as well. And the oxygens like sodiums and also composite materials. And then we have bromines and sulfide, carbons and oxygens and those kinds. And we also have this kind, the separate deconvoluted the carbon 1s, the CC, CO, COC, carboxyl groups like this. And also this is a carboxyl, the control CNC. This is a surface esterified CNC, and the different shift of the change the concentration, and also the composite materials. And this also have a carbon, bromine, and carbon sulfide together. So you can detect like this kind of spectrum by XPS. We also have the nitrogen spectrum here at the NCO, the amino group right here. This is the CNC over here, and EDC, and the reactive the cellulose, and the NDS, EDS, with the reactive the CNC here. And also the it's the ECNC with activated Pcb sulfur. We have sulfur like this, and the reacted here, and all sulfur groups here. And also interesting thing is right here, bromine peaks here. We have ECNC and activated Pcb and the bromine, and two peaks. One is reacted here, the other one here. That means these bromocursor purples are reacted at the CNC on the surface. So we also look at the morphology film with the SEM. The controls are very nice film, and the surface cross section. So 5% composite material ECNC and the activated BC a little bit rough, but the 10%, 15% is a little bit rough. Some materials aggregated in the matrix. So this kind of the problem is always happens in other polymers as well. And also we checked whether the activation of the BCP had any change in influence in the color changes using the UV visible spectroscopy. And we have this kind of BCP control and activated BCP, and put them in different purple solutions from pH 2 to 10, the same thing. And then we measure the absorption of these peaks, and then isospecific, the wave numbers are same, 48.9 nanometers. The activated, either activated or control the same. And also the same thing, normalized absorption is pretty same as activated BCP, and the control BCP is almost pH, PK, the associated little bit change, almost same. That means the activation is not much the impact on the color change of bromocursor purple. And then we made the films, and then we measured put them in the different purple solution from pH 2 to pH 10, different the levels of 5% composite materials and 10% and 15%. As you see, this is a control that activates the bromocursor purple only in the cellulose acetate film. But here, 5% is not much change in colors. This is not good. And then we have 10%, they're a little bit change in colors, and between 7 and 8 and 4.5, and the 15% it looks much better than the year. But this kind of the evaluation is very qualitative, and then we used quantitative measure using calorimeters. brightness and different things. And I just want to say that the delta E value, which is kind of color changes. You know, the delta E below the smaller than the 5 is undetectable by naked eye. Above the greater than the 5 of delta E is easily detectable with the naked eye. So when you see here, pH separation, nothing changes here. When you go to the acid, a little bit changes right here at the 2, 3, a little bit 4 right here. But in here, and the green is right here, is 5% control activated. They change a lot of the pH between 9 and 10. But the composite materials is about the 5-10%. It's a little change about 8 to 10. So they are changing colors. What I'm saying is that this the color change is quantified by expressed by quantitative numbers. And then we use delta E values for different pHs, and then this is the one, and then control is pH 10, and then here control is just 5% activated BCP. Here they only change the delta E value, dramatic change between pH 9 and 10. But here at 5%, 10%, 15%. 5% not much change, but there's slight change above the between 7 and 8. That means 5% the composite material in the cellulose acid film, we can detect the color change at between 7 and pH 7 and 8. And the 10% is much better than 5%. As you see here, between pH 4 and 3, there are big changes in color, and also there are changes between 7 and 8. We can detect, I would say, we can detect the colors of this film above pH 8 over here, and we can detect it. And also we have the 15%. That's a little change right here, left hand side, the low pH, but here is pH 4 and 5. pH 4 and 5 is a little change detectable, and also pH 7 and 8, above pH 8, we can detect the color changes. So that means if you have this film above pH 8, anyhow, some carbon dioxide or some other amines or some other things, and then change the colors above pH, we can detect the color in naked eye above pH 8. And also we check whether there is a color change reversible or not. So what we did is we have picked the pH 2 and pH 2 purple solutions, and then add the emerged in the solution 3 times, and then whether there are change color change or gone or disappear or something, and they control here, and then we put the first time in the about 30, we put emerged 30 minutes in the solutions, and then pH 2 10, and the second time it did 10, and third time, so not much change. That means this color change is reversible. It keep going as soon as the up to about 30 times. That means about 1.5 hours. And also we check the brightness of these films and the different pH 2 and pH 10. The 5% control and the 5% composite materials, 10%, 15% composite materials. There's not much change. You still the color changes are reversible. The brightness is as well as the delta E value. And also we checked any the reaching of the dye in this film. So what we did is we picked 10% EDC and 8% activated BCP. That means we use this composite material 10% added in the acetate film, and then make the film and then test them, and different pH 5, 7, 2, 5, 7, and they keep it up to 24 hours right here. This is pH 2, pH 5, pH 7, and the pH 10. And then this is and you check the UV if there are any changes. So this is nothing changes here, and the pH 5, the pH 2, pH 5, not much, and the pH is about 24, so a little bit change, not much. It's acceptable. But at the pH 10, about I would say about 3 hours, after 3 hours, they are releasing a little bit. So we need to avoid using this film above pH 10, you know. So this is kind of the leaching test indicate this result. And then I'm going to move the next things there. This is a cellulose nanofiber, which is prepared by temp oxidation and then mixed with the neutral red, which is also a kind of pH indicator. And then mixed with the polyvinyl alcohol as a matrix for making films. Right here, so you know, neutral red has amino groups, so that means we don't need to activate this pH indicators. As you know, neutral red change colors become yellow, below pH 6.8 becomes yellow, above pH 8.0. So we also use the same schemes like this, EDC, and then we have the EDC and the conjugated, and then we use NHS and the kind of the intermediate product, and then we make a reaction with a neutral red like this. Possibly we expect that this nanocellulose make reactions to amino groups, amide groups here with the neutral red. That's the one that we the idea. And then we take the FTIL. This is composite, and this is a temp CNF that's a neutral red. And then we check the little bit enlarged spectrum right here. There is a change of about 1600 wave numbers. Nothing in the changes like this. So as you see here, the neutral red right here control, and the red is the composite material. So they have different the wave new peaks here. They belongs to the amide group between nanocellulose and the neutral red. So this is the one that we confirm that there is a reaction between them. And also we check the color changes of this composite material CNF with neutral red, and here is you know, isospecific. The point is about 467 nanometers, and they also absorption like this. And also they have the PK is not much, that it is pretty same as the neutral red, and actually this one contains 0.5% CNF neutral red composite material in the the matrix. And also we did XPS analysis on the surface, what was happening. So here is a small amount of the chloride is possibly the temp oxidation, because temp oxidation uses sodium hypochlorite as an oxidant to making the films, making the cellulose CNF. And the C1, the carbon oxidants and the sodiums like this. And then you have the as a CNC, there's APS, I mean ammonium polysulfate oxidation CNC. They have carbons that deal with the sulfur and the chloride and the sodiums like this. And then we mixed the cellulose nanofibers in the neutral red together, and then we have, obviously we're gonna have the nitrogen because neutral red has contains nitrogen. And also we use also CNC here, and also nitrogens, because there's the neutral red contains nitrogen. And we also use, this is one example, the CNF only. CNF and the CNC had to have this kind of reactions like this, and then we got the concentration, the carbon 1s, oxygen, and then obviously CNF has no nitrogen. So sodium, chloride, a little bit, no sulfurs. But neutral red, we have carbons, and also obviously we have nitrogen, and our oxygen is decreased. That means we have some of the oxygen is gone to the reactions. So here, you write this, and I will say we have the cell nanocells has been reacted with the neutral red, this kind of amide groups, amide the bonds, I would say. And also we did the CNF and the XPS or the different C1S, C2, like this kind of analysis is control. This is a CNF neutral at the composite, 5% composite, and then we have this kind of shift changes, you know. And also, obviously, we have nitrogen peaks for the composite CNF and the neutral red composite materials. Like here, we have three different types of nitrogen environment, I would say. First is right here, pyridine, the red on the inside here, and pyridine nitrogen, and the torsion nitrogen here, and then amide nitrogen here. So this cumulative curve like this. That means we have XPS has clearly shows the nitrogen part, or also shows the amide bond between the nano cellulose and the neutral red. And then we used in this time PBA, polyvinyl alcohol. As you know, PBA is water soluble polymer. When you use it, it's soluble in water. So we don't want this kind of problem. So we use the polyalkylic acid as a cross-linker to make cross-link the PBA polymers. So we have a different PBA concentration from 5%, 20%, and then different heating as a cross-linking process, 15 minutes to 40%, 45 minutes, and the temperature is fixed at 170 degrees Celsius. And then we have this kind of film and the measured thickness, and depending on the cross-link PAA concentration from 3%, 15%, and 20% too much, and we just reduce to 15%. And also we measure the thickness, tensile strength, and the Young's modulus elongations at the break. So as you see here, when you have increased the PAA, obviously increase the tensile strength because they increase the cross-linking densities. But above 15%, it's a decrease. And Young's modulus a little bit decrease up to 10% PAA, but decrease later. But elongation obviously decrease of increasing the PAA concentration because it's used as cross-linker. And also we use to check the swelling and also water solubility of this film. As you see, as the PAA concentration increases, the swelling is decreased. That means when you more cross-link, you have less the swelling of the film. And also you have water solubility much less when you have the higher cross-linking agent in the PBA. But 3% a little bit soluble. This is kind of typical for us to solve this kind of PBA polymer as a matrix. Anyway, 3%, 5% is we try that to make the composite material. Here we use the 0.5% CNF and the neutral red, and then 3% PAA and 15% PAA different times. Just I showed examples. So these kind they have different colors that depend the pHs, and about 15% is not much color change because you know they have a very highly cross-linked. So idea is something like this, you know, this kind of things, we're gonna have this kind of film indicators for the food or something. And also we check the color meters, any color change of this film at 10 minutes, 20%, 20 minutes, 30 minutes, and the different buffer solutions like this from pH 2 to pH 10. As you see here, 3% PAA, it's a change in colors a little bit above, below the acid, above the pH, I would say 7. The change is delta E is much much clearly changed, but not much of 5, 10, 15%. So and the 20 minutes also big changes in the 3% PAA cross-linker. There's a little change on the 5%, and the 30 minutes half an hour that much change colors at the 3% PAA, 5% PAA, much better color changes at depending the pH above the below pH 5 and above the pH 7, they are changing colors. As I mentioned here, you know, below the delta, below 5 of delta E is you're not going to see the naked eyes of any change in color. But above 5, you can check to see the color change in naked eyes. So that means we can check all of these color changes with the naked eyes. Oh, okay. So up to now, I talked about mainly about the CNF or CNC-based composite materials which are able to detect the color changes depending on the pHs. Now I'm going to change to the hydrogels, the nanocellulose-based hydrogels. So first time what we did is we did the temp oxidation of how to bleach the craft pulp fibers, and then temp oxidations, and then we did the sonications at different times, 40 minutes or different times, and then we separate the top part. A supernatant becomes a cellulose nanofibril. At the bottom part is because cellulose microfibrils. Sometimes when you, the first time when you prepare the nanocellulose, you're not going to see the nanocellulose in naked eye. Even you have the beaker and the solid suspension, you're not going to see that. That means most of the nanocellulose on the top part, not at the bottom. Bottom is a bigger fiber, cellulose microfibers. When you need to nanocellulose, you use a top part supernatant, and then use for the further research. But when you have the microfibers, you can use a bottom part. So, and different sonication times, but they have the sodium carboxylic and nothing changes. And the carboxyl content group is controlled. But sonication time, microfibrils and nanofibrils are much higher, the surface charges to compare the microfibrils, but nothing changes over the different sonication time. The CNF yield is a little different. When you have the higher the sonication time, you have a little bit higher CNF yield. As expected, the cellulose, the suspension viscosity also increased over the higher sonication times. But nothing changes the crystal X-ray diffraction patterns. It's obvious because nothing changes in this kind of physical parameter. And also crystallinity, nothing changes sonications. And then this idea is very simple to make hydrogels. As you know, when you have temp oxidation, CNF has a surface negative charges, sodium carboxylated groups. And then you just add the cations, aluminum trivalent cations or divalent, or just the hydrochloric acid provide the protons. And then we add these kind of different types of the cations on the temp oxidated CNF solution suspension and the microfibers, and then we get the microgel, and then we also the freeze-dried the aerogels, and then we also same different types of the cations in the cellulose nanofibers, and we get the nanogels like this, much tighter the inter-impressionist morphologies. So idea is something like this. You have, when you do a temp oxidation, you have a sodium carboxylated group surface, which is a negative charge, and then you add the positive metal cations on it, metal cation, and then they have kind of the ionic interaction between the sodium carboxylate and the metallic cations, and then you can interfibrillar reactions, and then you make the hydrogen. You may try this; is very simple, So you can try it in the lab in your chemistry class as well, maybe. Okay, and then we look at the morphology of this, the hydrogels, the aluminum cation, calciums, and the protons, and the different structures of morphology, and the different. This is different magnifications, So this is much tight morphology, and this cation, but protons is very loose structures. And also we check the different types, they characterize different properties of these the hydrogels, different specific surface areas. As you know, these nanogels increases, but the nanogels right here. This is a nanogel at the triangles and the nanogel triangles, and the others are microgels. And also the suspension compression strength, microgel is bigger, and the nano compared to nanogels. Also, compression strength of the different cations. This is different concentration aluminum cation levels, 6 milli to 24. So we expected a little bit increase, not much, but 24 milli, the much bigger the period diameters. And the compression strength that also is much bigger the aluminum cation because they have a three valent the cations, so much bigger the arms, you know. And then we use these nanogels for the drug release. As we use the drug as hydroxythiopylene and put them in the thiopylene solutions, and then we check the release of these drugs over time, and also different concentrations, 0.2 by 0.6% surface charges, and also different. This is the CMF and the CNF, right? And the different types of the cations for CMF. These are different types of the cations for CNF. So they are a little bit slightly changed, but the CMF a little bit bigger changes in the drug release behavior. And the next thing is about also CNF-based hydrogel, but there's a stimuli responsive hydrogels. The idea is we combine the thermal responsive polymer, which is polynippon. They are changing the state in joule and the gel at the low critical solution temperatures. So idea is we combine the thermal responsive polymer with temper oxidized cellulose, this nano cellulose, which is CNF, with different surface charges using different oxidant levels, and then try to make the stimuli responsive hydrogel, which is responsive to temperature and also pH. That's the ideas. You know, when you have this kind of hydrogel, you have hydrogels and polynippon.
Your time is 5 minutes left. Sorry.
Oh, really? Oh, I'm going to finish quickly. So anyway, this is a hydrogel responsive to the temperature and also pHs. And then we use different amount of the oxidant levels to have different charge levels. And then we have different oxidant, different surface charge levels, and we check the FTIR, rheology, and the compression strength, those kind of things. And then we also use the different amount of nanocellulose in the composition in the polymer. And also we have different LCSSD and also polymerized which this is the radical polymerization, right? 11 degrees Celsius and minus 20 degrees Celsius to polymerize. And then we also measure the water retention and also the polymer, different polymer temperatures. We have also water retentions like this. So, and the swelling ratio is also changing on the different pHs, and the changes also the pHs, they also equilibrium swelling ratio also changes depending on different surface charge levels. And also we obviously critical the low critical solution temperature about 33 degrees Celsius detected by DSC. They also change the swelling ratio at different temperatures, minus 20 to the 60. Below the LCS is the swelling. Above the LCS, shrinked. And this is also we use a different polymerization temperature. We also using measure the swelling ratio depending on pH and also the pHs as well. Minus 20 is a little smaller swelling ratio than 11 degrees Celsius. This is what I'm going to tell you, that we prepare the hydrogels and then put them in the hydrogel 2 different temperatures, 25 and 37 degrees Celsius, and put them in 2 hours, and then measure the swelling ratios at each steps. As you see here, as time increases, this is 11 degree polymerization, minus 20 degree polymerization temperature, and 10% CNF. You know, they are swelling ratios up and the shrinking like this. We can have this kind of response, thermal response polymer. Up to, I would say about 10 hours is okay. But pH response is not good. We have two levels, pH 2 and pH 10. And the same thing, we put them into these hydrogen and these purple solutions, and then and check the swelling ratio. Swelling ratio not much changes, and the different polymerization temperature. That means this the hydrogen is very responsive to temperature. I would say less responsive to the pH. And also we try to use different the cations, coppers, the irons, make the hydrogels to have this kind of hydrogels. And then this time what I'm going to do is we have cations and then tempo CNF, and then we add the anthocyanin from the red cabbages. This is kind of also the natural dye, have this to detect color changes. You know, we prepare the hydrogels with anthocyanin, and then we expose to ammonia vapor gas, and then check any color changes, this kind of different these cations, and then they have different color changes. So this is one way to have detecting color change of hydrogels as kind of smart or the functional hydrogels detecting color change in the food or any materials. So this is kind of conclusion. I would say acidification is much better color change than amination. You know, the pH indicator is detectable color changes, and also we can make a successful indicator with SYCNC and the bromochloride purple, and also we have the ECNC with the bromochloride purple. 10 or 15% is okay. And the neutral lead also successful to making color change film. Also, we can detect the color change on this film. On the CNA-based hydrogels or DR responsive to temperature pH, but I would say much better for temperature rather than the pH. And also these relatives say that the Nano Cellulose based function must have a great potential as a indicator films in the future. Thank you very much for your kind attention. Thank you. This is the end of my presentation.
Okay. Okay. That's really nice presentation. Thank you for Professor Byung Daik Park. Now we are in the question session. And interesting, many questions has been submitted on chat. Let me start with the first question. Let me first, we check the first question first on the chat. Yeah, came from Malang State University, from Lina Maziatus Salma. There are various sources of nanocellulose. In the study, what are your considerations in choosing a source of nanocellulose? And what is the effect on the isolation process?
Yeah, that's a good question anyway. You know, you can use different, various different sources of nanocellulose using wood or cotton or some canap, those kind of things. But the important thing is that gives a different natural variation of nanocellulose. And on top of that, one of the important is what kind of the method you're going to use. When you use the acid hydrolysis, you're going to kind of nanocellulose crystal, which is a whisker. But when you have the APS or temp oxidation, you're going to have the fibrillary structures. So, and then that means the combination of the what kind of source you're going to use, what kind of the method you're going to use to isolate nanocellulose, very important. But on top of that, I want to say that there is in Korea or in the United States, they provide, in Canada, they provide a commercial nanocellulose from wood. I would say in Canada, they provide the cellulose nanocrystals, which is prepared by acid hydrolysis. And also in Korea, we also provide some of the company, Hansol Paper Company, they also provide a temp oxidized CNF in the commercials. You can also use that. Also in the US, they also provide the CNF, also CNC from a pilot plant. So you can use also that. But You can also use oil palms, those kind of things. You can use that, and then you pick proper the method, acid hydrolysis or APS. I would suggest if you have a little bit the lignins, hemicellulose, and then you may use APS to get the nanocellulose quickly. If you have the lignins and in the raw material, temp oxidation is very hard, but the CNC acid hydrolysis is a little bit okay. Is that the good answer for enough the answer for the question?
I thought yes. Is it okay? Yeah.
Yeah.
Okay. Prof, there is any second question from Mr. Saifullah from our university. They mentioned that nanocellulose seem very promising for its very wide application beyond its abundant availability, biodegradable, ubiquitous, renewable, but to produce it require chemicals that are not environmentally friendly in large quantities. So far, it is a pilot plant to mass production in order it produce it on Earth. Thank you.
Okay. As I mentioned, there are some the pilot plant in the Canada, Cellular Force, which is based on the Montreal in Canada. They have the pilot plant. They are selling CNC, which is based on the acid hydrolysis, and also the University of Maine in the US. They also have pilot plant. They also provide the commercial CNC, which is based on acid hydrolysis. And also in Japan, also there is the pilot plant. It's commercially available in the CNC or CNF. I don't know exactly, but also in Korea, there is available the CNF based on temp oxidation. So you can use this kind of the commercial ones for your research. If you need further information, just contact me, send me the email, and then I can arrange for your contact. Is that okay?
Is there a further question, Mr. Saifullah? Oh, that's enough. Okay. We have a little bit, 5 minutes more, the time. And I thought that's for further question that's from Novera. They criticize that regarding the mechanism of the color change of this nanocellulose according to pH, since usually such pH sensitive or responsive polymer has a functional group which can protonate or deprotonate, but in this case, in the form ester has better color change. What's kind of the reason?
I'm sorry, is it the second part?
Yeah.
Right here.
Yeah. The
first part.
Yeah.
Oh, okay. Yeah, that's a very good question. As I mentioned, why I use the nanocellulose for detecting color changes or pHs, because you can use the pH indicators. You can put the pH indicator in the water, and you can different pHs, and then you can change color. You see the change of colors. But what I'm thinking about is I try to make a kind of indicator film or a film indicator. In that case, you can mix pH indicator with something or polymer. In that case, you have to think about how maybe a pH indicator dye may be released from the matrix. This is not good when you are using the film or indicators. So as you mentioned, the nanocellulose is a crystallized cellulose. It's suspendable in the water. They are hydrophilic, but they are not dissolved in the water because they are crystals. Even water molecule is not able to go into the nanocrystal because they are crystallized. They have very, very tight hydrogen bond. Water is not able to go into the cellulose. So the idea is I use the nanocellulose as a carrier because nanocellulose, CNC or CNF, have carboxyl groups on the surface, which is easy to make esterifications. So that's why I use the nanocellulose, and then make it react to the pH indicator as a carrier, and then make this film, which can be used as a kind of as an indicator in the future, or in the future pool storage or those kind of things. So what I'm saying is that you can, if you have any solution using pH indicator without the nanocellulose, without the releasing, without the reaching, you have that you have better than me. You can find that. That's good things. But it seems to me when you have a pH indicator in the itself, it may be soluble in water and then it released. That's the going to be problem in the future. That's why I use the nanocellulose as a carrier for this kind of the functional materials. Is that enough?
Yeah. Yeah. I'm sorry that there is the third question that I didn't mention yet.
Okay.
Please. Sorry about that.
No problem.
Okay, I jump to the number 4.
Okay.
The question that's we have universal or paper-based pH method to detect pH. I couldn't catch the message why you use cellulose nanofiber to detect pH. Could you please explain the impact?
Yeah, that's what I said, you know.
Yeah.
I answered these questions.
Oh.
What I'm saying is, as I mentioned, the nanocellulose is used as a kind of carrier.
Okay.
Not the kind of reactive materials, because pH indicator is, most of them is water soluble. When you use this pH indicator, any kind of material, when you contact the water, that is dissolved and then it can release the leaching. That's problem. So in order to prevent any leaching or soluble in the water, I have to make a reaction, a very strong bond between the nanocellulose pH indicator, and then you have no problem for leaching.
Okay.
Yeah.
How about number 4?
Oh, this is at the bottom?
Yep.
Okay. Oh, I can read it. Can you please put them on again?
I have a question regarding the mechanism of color change of this nanocellulose according to pH, since usually such pH-sensitive responsive polymer has a functional group which can protonate or deprotonate. But in this case, in the form of ester, has the better color change. What's the reason?
Oh, what I'm saying is I use the acidification amination. What I'm saying is the surface multiplication of nanocellulose using acidification is much better for the making reaction with the pH indicators. Amination is not good. I don't know why, but probably one of the reason is, you know, as you know, the pH indicator changing colors depending on the pH, because protonated or deprotonated, as you know. But yeah, aminated means aminated CNF or CNC is not good for the protonation. That's why they're not good for the color changes. But when you have acidification modified surface of cellulose, it's much better to make a reaction with the pH indicator, and with this attach the pH indicator much easy to moving around deprotonation, protonation, those kind of things, and then give a good color change. That's what I think.
Okay.
Yeah.
Okay. This time is already finished, and thank you very much for your nice presentation. And we would like to give big applause for you and your nice what we call it, familiar.
Thank you very much for inviting me as this wonderful conference. Have a good time. Thank you.
Thank you very much. That's really a tough presentation and very tight schedule also. So we have to move to the presenter. our time that's for Dr. Hasliza Bahruji. Yeah. She would like to share his experience and his research project with the title that's carbon dioxide hydrogenation to C1 and C2 plus hydrocarbon using bimetallic catalysis PDZM. Firstly, we'd like to also inform you the CV of Dr. Hasliza. Yeah. He got bachelor and master degree from University Technology of Malaysia and finishing his PhD at UK Cardiff University. She well known is a multitasking academician with 15 years experience in university, both as a lecturer and researcher. She have developed extensive research network with researchers in UK, US, Japan, Spain, Indonesia, and Malaysia. He also experienced lecturer with the expertise in designing curriculum, teaching and supervising undergraduate and master students. Have wide knowledge in nanoparticle and material synthetic and heterogeneous catalysis, particularly for sustainable renewable energy production and environmental pollution. She has also published so many papers, and we couldn't read his further CV. I thought that's enough for us to know our keynote speaker. And now that's your time, Dr. Hasliza Bahruji.
Hello, Assalamualaikum.
Waalaikumsalam.
Let me share. I want to share my screen, but yes, I will. No. Let me share my screen. I cannot actually share my screen. Can you allow me to share my screen, please?
Dr. Hasliza, you are a co-host, so you can directly share your screen. It's not permitted by the system.
Okay, okay, yes. Wait a minute. Yeah, can you see my screen now?
Okay.
In the process. Okay.
Yes.
Yes. Okay. Wait a minute. Okay. So today I'm going. Assalamualaikum and very good morning. First of all, thank you very much for the organizer, especially Pak Anto, which I known him since we were working together in UK Catalysis Hub a few years ago. And thank you for giving me this opportunity to speak in the Third International Conference on Chemistry and Material Science by University of Jember. So a little bit of introduction about my background. I'm Hasliza Bahruji. I'm currently working at University Brunei Darussalam, which is a Center of Advanced Material and Energy Sciences. And the talk that I'm going to share for today is actually based on my work that I have carried out in UBD and also from my previous employment in Cardiff University. So what I'm going to share today is basically, we're going to look at palladium zinc catalyst for CO2 hydrogenation to methanol, dimethyl ether, and also C2, C5 hydrocarbons. Sorry. So just to start, I've divided my talk into several outlines. First, I'm going to talk about CO2 hydrogenation to methanol, and this will include discussion on palladium on zinc oxide as a catalyst, and also how we modify the catalyst by create or produce palladium zinc alloy on titanium catalyst. And then we're going to explore a little bit more on what more can be done, and this is include how we can define thermodynamic equilibrium by using bifunctional catalysts, which essentially we're going to try to put palladium zinc alloy on ZSM5 as a support, which we combine the metallic palladium zinc, bimetallic palladium zinc, and also this Bronsted acidic ZSM5 as our acid catalyst. And then we're going to move further towards understanding how CO2 can be further hydrogenated to dimethyl ether by using palladium zinc ZSM5 catalyst. And then the reason why we're doing this is because we try to enhance the production of oxygenated products, especially for reaction at much higher temperatures. And finally, we look at the possibility of us try to convert CO2 towards much higher hydrocarbon, which in this case, we're going to have a look at the hybrid catalyst between palladium on titanium and the ZSM5 catalyst. And this gives us understanding on the potential of utilization of CO2 as a carbon source for direct production to biofuels. So this is a general introduction, why we are really interested to look at the possibility of use CO2 as carbon sources into a useful renewable products. First of all, we know that our activity as a human, that we are have this sole dependency on fossil fuels as our primary source of energy, that it actually been consumed and converted into carbon dioxide as the end products. And this carbon dioxide, if you look at since from 1990 up to 2040, it was predicted to continuously increase. And when we look at the in January 2040, what we see is the amount of CO2 that was produced is actually surpassed the irreversible target, which is by this point, the CO2 that was actually present in the atmosphere will no longer be reversible. So it has to come down to us as a human to find a solution, how we can reduce the rising level of CO2, and at the same time, can we manipulate the CO2 as the abundant abundant sources of carbon to something that is beneficial, which is fuels. So, of course, as in general, I mean, when we think about CO2, the best way for us to reduce the concentration of CO2 in the atmosphere is by planting more seeds to produce trees, or to stop cutting down more trees. And then this allows the CO2 to be used by plant, by photocatalysis. This is the way that Allah intended us to do. And then this CO2 is basically being converted into energy in terms of glucose by absorption of light. This is in principle what we as the community, as a world population has to be done. But as a scientist, we also have to do something more. Can we absorb the CO2? Can we utilize the CO2 and convert them into products that can be beneficial to us? So this is what we try to propose. Can we actually convert CO2 into methanol, which essentially will we will achieve this closed carbon cycle? We know that CO2 was produced based on the consumption of fuels to get to carbon dioxide. If we can convert CO2 back into fuel, basically we achieve a closed carbon cycle. So currently, methanol was produced, is a top 10 commodity chemicals, and then it produced basically from a synthesis gas, which is a mixture of carbon monoxide and carbon dioxide and hydrogen. This synthesis gas is actually derived from natural resources, natural gas through steam reforming, and then the reaction normally require copper zinc oxide, maybe on alumina or scandium oxide as a support. And then the important bits of this catalyst is to improve or to increase copper dispersion and which will determine the activity for methanol production, and at the same time will try to reduce the sintering of copper nanoparticles on the catalyst surface. And why methanol is very important? This is because methanol is a raw materials for the production of olefins, for example, from methanol to olefin reaction, or for the production of gasoline, for example, from methanol to gasoline production. So not just that, it's not just CO2 as a main carbon sources. CO2 has also a potential to be the hydrogen storage, especially when we talk about transfer of hydrogen, which is a very flammable gas. And then when we use CO2, carbon dioxide, as a storage, as an agent to capture or stabilize the hydrogen gas, and then it can be easily transferred into our different type of facilities and improve the accessibility of hydrogen. So this is basically the reason why we want to explore the ability of CO2 to be converted into methanol. And then this is the main idea, which is we start with the CO2 capture basically from the power plant. This is the main source of CO2 generation. This power plant, the CO2 will be captured and will be fed into our methanol synthesis plant. But the most important thing, providing that the hydrogen that we get actually comes from a sustainable and renewable resources. For in this case, we propose that hydrogen comes from water electrolysis based on the wind energy or solar energy. And the methanol that been produced can be further transformed into fuels, whether for household or in the power plant itself or in the vehicle or transportation. This is the main idea. If we manage to achieve these routes, which is an efficient catalyst that can convert CO2 into methanol at a kind of like ambient condition, like an economically viable condition, which will give us this closing carbon cycle system that will not release CO2 into the atmosphere anymore. So this is what we have in our laboratory that we designed that allow us to screen our catalyst at certain temperature and certain pressure. Basically, the reactor setup involve this catalyst bed, which is our tubular furnace, that we have our catalyst inserted in our catalyst bed by stainless steel tubing, and then everything. We have a flow of hydrogen gas. This is very crucial for our pre-treatment of the catalyst. And also we have our mixed gas. In this case, we varied the ratio of the mixed gas from 1 carbon dioxide into 3 moles of hydrogen, and we have the nitrogen gas as a balanced gas. And then all this product will be, the pressure of the catalyst will be controlled by this pressure back pressure regulator, and then further analysis will be conducted using DC analysis. So this is basically a simple setup that allows us actually to screen the catalyst from 0 to 50 bar, at the same time from 50 degrees Celsius up to 450 degrees Celsius. So when we talk about CO2 hydrogenation to methanol, there is always 2 competing reactions, which is the first is CO2 hydrogenation to methanol, and this has its negative delta H and also a positive delta G that give us this reaction is not spontaneous reaction, and it favors a low temperature but at high pressure system. But the competing reaction that we always have to deal with is reverse water gas shift reaction, which is a reaction of CO2 with hydrogen, but instead we get this carbon monoxide. And this experiment, this reaction is actually only is a positive delta H value and also positive delta G, which is it always favors reaction at high temperature and low pressure. So this is our thermodynamic studies that we look at how CO2 actually behave at 250 degrees Celsius, but by varying the pressure of the reaction. So basically, the red plot here tells us that CO2 hydrogenation to methanol, and the black plot here is CO2 conversion to carbon monoxide via reverse water gas shift reaction. What we can see from theoretical calculation here, when we increase the pressure from 10 bar up to 100 bar, we can see that the temperature, the conversion of CO2 is actually favoring methanol production, but it's not so much for carbon monoxide. It tells us that in order to achieve high conversion of CO2 into methanol, the important key is to have high pressure system. But when we stick or we maintain the pressure up to 20 bar and then we vary temperature from 470 up to 580 Kelvin, what we can see, this is a complete opposite from the increasing the pressure. What happened is the product mainly will produce into carbon monoxide, but not methanol production. So we know that we have to be very careful in setting up our reaction condition. The pressure and temperature as well will actually contribute into the activity of the catalyst. So apart from methanol and carbon monoxide, we have also another third competing reaction that basically depending on the type of catalyst that we choose, which is a methanation process, which in this case CO2 will react with hydrogen while producing methane and water as a byproduct. So this is all type of competing reaction that we have to take into account when we try to design our catalyst in order to achieve high methanol productions. So we start with palladium catalyst. Why we're really interested with palladium? Because palladium has this unique deep band structure that allows us to modify them, convert them into alloy, or stay itself as a palladium metals that has a good ability to dissociate hydrogen for hydrogenation reaction. So we have done so many works on palladium before, and when we started to work on this reaction CO2 hydrogenation, we try to put palladium on different type of metal sulfide. In this case, we use zinc oxide, we use gallium oxide, tin oxide, titanium, alumina, and ceria. Now, what we can see here, the products mainly carbon monoxide and methanol. But when we have titanium and alumina, we'll be starting to see methane also being produced. So it tells us that the competing reaction is carbon monoxide and methanol. But methane is only produced when we have a certain type of metal, certain type of active site that can actually create this methanation active center. And we look at CO2 conversion, some of them is very active, for example, palladium and zinc oxide, some of them not really good, for example, tin oxide and alumina, but when we have ceria, we also have a high conversion. The differences between this type of support is the selectivity toward methanol. The only catalysts that have this high selectivity as well as high conversion to methanol is palladium zinc oxide catalyst. So this screening process allows us to easily pinpoint the best metal oxide that can be further investigated to improve the selectivity towards methanol at kind of like mild reaction condition. Bear in mind that the reaction condition that we have is only 20 bar, which is quite mild compared to industrial condition, which is normally 50 bar. So we try to understand why palladium zinc oxide is very active. So what we did, we increased the reduction temperature from 120 degrees Celsius up to 700 degrees Celsius. The SOFD peak that we can see here is actually tells us that there is a there's a transformation of the active site of the catalyst from reduction at 120 up to 700 degrees Celsius. At the very beginning, the palladium actually exists as palladium 0, which is in the metal zero oxidation states. But when we increase the temperature up to 400 degrees Celsius, we can see that the formation of palladium zinc alloy starting to observe. The shift of the diffraction angle towards higher diffraction angle gives us an indication that this palladium is actually transformed into palladium zinc alloy. And when we increase the reduction temperature even further, up to 700 degrees Celsius, we can see these two peaks is actually produced, tells us that palladium zinc alloy is completely formed from this catalyst. When we also support the observation by looking at Tdm analysis, which we see that the nanoparticles that was produced here around 3 to 4 nanometers, and the lattice spacing was identified around 2.185 nanometers. That tells us that this is indeed palladium zinc 111 nanoparticles. Then we also carried out Xps analysis, and when we have this catalyst that was dry in air at 500 degrees Celsius, the catalyst is actually present as palladium oxide metal, palladium oxide metal oxide. So, but when we reduce that at 400 degrees Celsius, we started to see the shift of the binding energy towards much lower binding energy. It tells us that there is a changes of electronic density of palladium, which give us indication it produced palladium zinc alloy. The same thing with the XPS analysis of the zinc LMM spectra that shows that the formation of palladium zinc alloy by the formation of zinc metal, zinc reduced zinc species here at 490 EV. So it tells us that palladium is a good hydrogenation catalyst, but since the reaction carried out under the presence of hydrogen, the hydrogen spill over caused zinc oxide to segregate and then transform palladium into beta palladium zinc alloy. And this palladium alloy is actually the species, the active site that is responsible for CO2 hydrogenation to methanol. So we try to understand the transformation of palladium oxide, palladium on zinc oxide to palladium zinc alloy by carrying out in situ experiment. So basically what we did, we start with the palladium on zinc oxide catalyst at 150 degrees Celsius, and then we slowly raise the temperature up to 300 degrees Celsius, and then we monitor the conversion of CO2, the black dot here, and also the selectivity towards CO, which is the blue dots here, and also the selectivity towards methanol, which is the red dots here. So what we see, interestingly, the CO2 conversion is quite similar from 150 up to 350 degrees Celsius. But the selectivity vary greatly. So at the very beginning, the catalyst is very active toward carbon monoxide production. This is because the catalyst itself is still on palladium nanoparticles, not palladium zinc alloy. But when we slowly increase the temperature up to 250, we're starting to see that methanol is starting to develop. And at the same time, CO selectivity start to reduce. And it gives us indication that the alloying process occur at the same time of the reaction being progressed, and that it slowly transform palladium nanoparticles into palladium zinc alloy. And when we reach 250 degrees Celsius, this is the optimum value that gives us high selectivity towards methanol, but reduce the CO quite tremendously compared to 150 degree reaction. But when we further increase the reaction temperature up to 300 degrees Celsius, this is when we're starting to see the CO was produced quite immediately or quite significantly compared to methanol. The reason why this happened, although we already produced palladium zinc alloy, is because of the thermodynamic restriction that I have discussed previously. So at high temperature, no matter active your catalyst is, it's always going to convert your carbon dioxide into carbon monoxide because of the thermodynamic restriction. We will no longer produce methanol. So when we look at the in situ analysis using SRD, we can slowly see the transformation of palladium to palladium zinc alloy when we increase the reaction temperature up to 400. That gives us indication, a proof basically what happened to the catalyst when we carried out the reaction from 150 up to 300. The important part is the transformation of palladium nanoparticle to palladium zinc alloy. And then we're going to study the mechanism why this is very important. This is because palladium zinc alloy is actually, this is what we did. It's very simple TPD process. We saturated the catalyst with methanol, and then we just ramping up the temperature up to 400 degrees Celsius. And when we monitor the product that we get when we increase the temperature, what we can see here, well, on palladium zinc, on zinc oxide catalyst, we have this coincidence peak showing the desorption of hydrogen gas and carbon dioxide. But when we have palladium not on palladium zinc alloy, we only see the desorption of CO and hydrogen. What tells us that the desorption of carbon dioxide and hydrogen implies the formation of formed species, which is only detected on palladium zinc alloy, not on zinc oxide. It gives us indication that the importance of palladium zinc alloy to actually stabilize this formed species during CO2 hydrogenation to methanol. And then this is how we improve the properties of the catalyst by increasing the reduction temperature. And we can see that the most active reaction is at 400 degrees Celsius that give us high conversion and high selectivity. And then when we investigate the influence of synthetic method to produce or to control the palladium zinc particle size, we look at when we prepare the catalyst using immobile impregnation method, and then we compare with salt immobilization method, we can see that the agglomeration or the sintering effect was a lot more negligible, or we cannot really see the enlargement of the particle size when we produce the catalyst using salt immobilization method. Why particle size is very important is because when we manage to control the particle size very, very small, we will ensure the catalyst will have high productivity towards methanol. And this is another way that we can design the catalyst, which is using chemical vapor impregnation. The benefit of this method is it gives us a solvent-free method that can create palladium zinc alloy. And then we also managed to produce palladium zinc alloy on titania, alumina, and different type of support that give us, we can increase the activity when we add them on titania. And then the reason why we use different type of support apart from zinc oxide, because as we show that from X2MS, there is always segregation of zinc oxide to create this palladium zinc alloy. So when we produce palladium zinc alloy on titania, we stop the tendency of zinc oxide as a support to keep donating zinc to produce zinc alloy, and this will restrict the enlargement or the growth of palladium zinc alloy. So when we have a look at this phase, we can see that palladium zinc alloy exists in different composition with a broader stability region. So basically, palladium zinc alloy can exist in different concentration. It doesn't have to be 1 palladium to 1 zinc ratio. It can have this range, which is from 0.4 to 0.62. So we try to vary the ratio of palladium to zinc alloy to see if we can improve the activity of the catalyst. So what we did here, palladium zinc on titania, vary the ratio of palladium to zinc at 1 to 1, 1 to 2, 1 to 5, and 1 to 10. And we have a look at the activity for methanol production, and it clear that at 1 to 5 ratio, we managed to improve the selectivity and the productivity up to 1,700 productivity an hour. And then at low zinc loading, we have lack of activity, and if we go into much higher, and then we also reduce the activity. So when we look at the effect of palladium zinc concentration on the size of particle, we don't really see any big differences. So basically, the particle size is around 1 to 6 nanometer, with the average nanometer, the average particle size exists as 3.4 nanometers. This is what we found when we tried to vary the concentration of zinc for the formation of palladium zinc alloy. This we have discussed this a while ago. And then when we reduce the thing with titania, from the very beginning, I'll show that palladium on titania, what happened is you produce methane. So methane is another competing reaction that will give a trouble to industry, because we need to be separated from the reactant gas in order for the product to be collected. So ideally, we like not to have any methane in our reaction. So what we can see here, when we reduce the reaction temperature up to 700, we manage to maintain the generation of methanol, but at the same time, we reduce the production of methane. So it's very important that we reduce our catalyst so that we prevent the production of methane. This is another example that we can also transform our catalyst support from titania to zinc titaniate. By having zinc titaniate, what happens is we suppress the methane production altogether. This is another indication that if in a certain type of experiment that requires us not to have any methane, we have to transform our titania support into zinc titania support that can completely remove methane from the reaction. So what more to be done? We know that our palladium zinc catalyst is very active to generate a methanol from CO2, but it always being restricted by thermodynamic So can we put palladium zinc alloy on our solid acid support in order to increase the production of oxygenated products at high temperature? So we try to defy thermodynamic limitation by carrying out experiment to conduct CO2 hydrogenation further to dimethyl ether. So what happened is, this is the equilibrium, the theoretical product that we can obtain when we use the palladium zinc or palladium zinc oxide catalyst, where we can see that up to 250 degrees Celsius, no matter how active your catalyst is, you cannot actually surpass the equilibrium restriction. But when we try to compare the theoretical production of DME and methanol, we can see that DME has much higher threshold, so that we can always push the temperature a lot further and produce these oxygenated products at much higher temperature. Because to reduce the reaction temperature is quite difficult, because CO2 is a very active molecule that requires quite high temperature to activate. So we have to transform the catalyst, instead of producing methanol, but we try to produce a dimethyl ether. The idea is we will intercept methanol by converting to DME or higher hydrogenates, carbon oxygenates that can overcome thermodynamic restriction. So this is the catalyst. We try to deposit palladium zinc alloy on ZSM5 catalyst, and then we can see that the particle size is around 5 nanometers, which is not much different from the deposition on zinc oxide or titania. Then we confirm as well the formation of palladium zinc and palladium zinc interaction by using Xps Analysis. And then when we conduct our experiment from 220 up to 340, and when we look at the conversion on palladium zinc on titania catalyst and palladium zinc on ZS5 catalyst, the conversion is pretty much similar. So there's not much differences on the activity of the catalyst to convert CO2. But the main important is how, by adding ZSM5 as a support, we actually managed to improve the reactivity of the catalyst to convert CO2 to oxygenated products, which is methanol and dimethyl ether. We no longer produce high concentration of carbon monoxide. This is very important. It tells us that yes, we managed to intercept methanol and convert the methanol further to dimethyl ether instead of reverse water gas shift reaction. And we can see that at 270 up to 300, we actually defy the thermodynamic, because a quick interception of methanol is actually give the edge of equilibrium process to actually push the equilibrium towards the production of dimethyl ether and methanol. So this is what the summary of the results so far, and then we can see we achieved 17% of CO2 conversion at 275, and the productivity is actually improved. We got like 2,000 minimal of oxygenated products compared to 1,700 when we only use palladium zinc on titania. And then the same thing as well, when we increase the reduction temperature, we actually maintain the DME production, but at the same time, we remove methane. And then what happened is, CO2 hydrogenation actually occur on palladium zinc alloy. The methanol will be transferred into ZSM5 support. This is where the dehydration process is occur, which is a continuous dehydration of methanol into dimethyl ether that allow us to actually defy the thermodynamic restriction. And then the catalyst is also stable up to 14 hours, and then there is no obvious agglomeration of the particles. When we carry out the experiment for a long experiment, basically the palladium zinc alloy is stable. We managed to stop sintering from occur, and it also has high stability with ensure high conversion towards oxygenated products. So what else can be done? So we already done CO2 hydrogenation to methanol. We try to investigate further CO2 to carbon 2 and carbon 5 hydrocarbons by using palladium zinc on titania hybrid catalyst. So what we did is we carry out the experiment. This is on palladium zinc titania only. And then when we increase the reaction temperature up to 360, we're starting to see the red one over here is the methanol production. At the low temperature, methanol actually favors the reaction. And then until up to 300, where it's starting to drop to give more methane formation. And some of the DME production. Okay, so more methane, and this one is a conversion. The conversion is always increased with the reaction temperature. It just the selectivity will be reduced. So what we try to do, we actually just physically mix palladium zinc on titanium as a catalyst with different type of ZSM5 with ZSM5 at different variation of silica to alumina ratios. So we have our palladium zinc titanium here. The main product that we have is carbon monoxide, yes, and then we have some methanol. This is, bear in mind, this is conducted at 270 degrees, which is not ideal temperature for methanol production because of the thermodynamic restriction that favors carbon monoxide formation. So we have this methanol quite very, very small amount, and then we have a tiny bit of DME. And when we added ZSM5 at 80:1 silica to alumina ratios, this is when we started to see methanol being produced, methanol being reduced, but we started to produce a lot of DME, and then we also try reduce the selectivity towards carbon monoxide. When we have silica to alumina 50, we are the same, basically similar observation, but we will reduce further to 23, and I'm starting to see this kind of product, which is a mixture of propane, ethane, and other hydrocarbon products. This gives an indication there is a possibility for us to actually convert our CO2 directly into fuel, which is olefin or paraffin mixtures. This is basically a hydrocarbon that is going to be beneficial for fuels. And then when we vary the reaction temperature by using this hybrid catalyst, palladium zinc oxide with ZSM5 with silica to alumina ratio 23, what we see here, DME is starting favor the reaction at low temperature. When we increase the temperature even further, we're starting to see a mixture of methane and then ethane, which is carbon 2 products. And then we also see this green one, which is the methanol still produced, and then a mixture of butane, transbutane. So there is a variety of possibility here. It tells us that the catalyst has the ability to catalyze carbon-carbon coupling reaction into longer chain hydrocarbon. This is just a preliminary works that we have conducted. It will be nice if we can, what we are trying to do next is how we can control the selectivity of this catalyst to obtain certain type of carbon-carbon hydrocarbon, longer chain hydrocarbons. And then we also look at the stability of the catalyst. And then this is Xps Analysis, very interesting method to allow us understanding into the depth within the palladium atom itself. And then what we can see here, there's not much different. So the black one is palladium zinc titanium that has been reduced, and the red one is palladium zinc titanium that after reaction. And we can see that there is not much different in terms of the coordination number of palladium metal. It tells us that there is no enlargement or the growth of palladium zinc nanoparticle when we have reaction at long temperature. And then when we do the SRD analysis before and after reaction, it's basically quite similar. Palladium metal, we still see palladium metal, and then we still see as well palladium zinc alloy and palladium zinc alloy nanoparticles. And it tells us that the stability of the catalyst for reaction at high temperature and longer reaction. So it has its high thermostability under reaction conditions. So there is the potential for palladium zinc alloy to be explored further, even though it's very expensive, but the activity, the stability at high temperature give us this edge for palladium zinc alloy can be utilized as a catalyst for direct CO2 hydrogenation to methanol. So I'll try to end I think I've done my 40 minutes. I'll try to conclude my talk, which is palladium zinc alloy is an active site for CO2 hydrogenation into methanol. The reason why it's very active because it has this ability to stabilize formate intermediates. And then the deposition of palladium zinc alloy on acid support ZSM5 allows us to actually tune the selectivity of the catalyst instead of producing methanol, but we shift the equilibrium up to we shift the activity to produce dimethyl ether, and then it increases the CO2 conversion into oxygenated yields. And then the combination of palladium zinc on titanium with as a methanol synthesis catalyst with ZSM5 zeolite as a hybrid catalyst actually allow a consecutive CO2 hydrogenation to methanol, DME, and also methanol to dimethyl ether in one cell, one single bed reactor. So basically, there is so many possibility to modify, to understand the balancing alloy itself. So far, we don't really know the actual role of zinc oxide and actual role of palladium monometallic that always presents with palladium zinc alloy in terms of promoting the activity of the catalyst. So the synthesized like olefin undergo further hydrogenation to corresponding alkanes, and then we can increase the future ability is we can always increase the concentration of aluminum on the SM5, and we can look at how it is affect the selectivity of the catalyst. So as I've mentioned, the work that have been presented here is the work that have been done in UBD and also from my previous employment in Cardiff University and Cardiff UK Catalysis Hub. And very much thank you from my former collaborator and former colleague, Prof. Michael Balker, Prof. Graham Hutching, and Dr. Jonathan Rees-Escris. And thank you very much again for this opportunity. I hope what I share today will have this benefit to you, and I'm welcome everybody to contact me if you want to start any kind of collaboration. So thank you very much again. Assalamualaikum.
Waalaikumsalam. Thank you very much for your presentation, and very attractive, yeah. For the when we talk about the catalyst, and it is now that's a question session. I thought there is many questions already in the chat, so no worries. So the first question is why you prefer methanol than methane as the product? The second, is possible to remove methane by membrane in high pressure during process due to the tiniest molecular size of methane? That's the first question.
Yes. First, why we prefer methanol over methane? So we need to remember methane is actually also the starting materials to produce syngas. So basically, if you convert CO2 to methane, you have to convert methane again into syngas, and then syngas into methanol. So you have these multiple routes of reaction in order to generate methanol as our main molecule that can be converted into fuels. But when we have generate CO2 up to methanol, basically a single step method for generation of fuels. That's why we want to generate methanol compared to methane. Besides, when you look at the equilibrium reaction, so the stoichiometry of reaction, for formation of methane is actually require 4 mole of hydrogen, which is hydrogen is the valuable part of this reaction, to be honest. But when we have to produce methanol, when we produce methanol, it's only required 3 mole of hydrogen, which is we reduce the amount of hydrogen that we require to reduce the carbon dioxide. Is it possible to remove methane? Of course, it's always possible to remove methane. It's not a problem at all. The problem here, the cost that we have to add in the operation system. Okay, if we need to separate methane, we require a membrane separation. Of course, another tedious method to actually absorb or remove methane from the system. So it's very easy for us. It's very convenient if we can stop methane production altogether rather than separating them at the end of the process. Thank you. I hope it's clear.
Okay, I said that's clear. The second question is from Suwardianto, our colleague here. Any possibility to substitute palladium with another transition metal that not considered as precious metal?
Yes, actually, several metals can be used for CO2 hydrogenation. Methane, nickel is very good hydrogenation, methanation catalyst, but the selectivity will transform into methane, not methanol. We can also use copper. Copper is quite interesting, but the problem with copper, you normally have a problem to increase the dispersion, and also it always have this sintering. I mean, because copper can absorb hydrogen quite well compared to palladium. The problem with copper, it always sintered over a long reaction and then it gives us low in activity. Yes, copper is a cheaper alternative. There's no doubt about it. But having palladium, it gives us much better selectivity and stable catalyst. Yes, you can always use copper. Yes, no problem.
Okay, I thought that's clear. So the answer. So we next to the further question. From you, Aris, that's my colleague also from University of Jember. What is the transformation reaction step of the catalytic carbon dioxide to methanol?
Yeah, as we show in our TPD analysis, the first important part is CO2 must be absorbed on the surface. So while it absorbed, normally it will form this bidentate carbonate, which is can be reduced by hydrogen that was dissociated on the palladium surface. So this bidentate carbonate will be transformed into this intermediate that we call as formate intermediates. This formate intermediate is very important because this is the key point, whether it will be transformed into methanol or it will be converted into carbon monoxide. So if you have this palladium zinc catalyst as an active center, it allows formate intermediate to be stabilized long enough for another hydrogenation to occur to convert formate into formaldehyde and finally to give methanol. So this is basically the reaction step from CO2 to methanol. CO2 from bicarbonate into formate into formate into formaldehyde and into methanol. That's basically what we understand so far.
Okay, that's a short question. So maybe this one is longer. Why use metal oxide catalyzed instead of metal catalyzed in the hydrogenation reaction to produce methanol as fine chemicals product? What is the difference between a metal oxide catalyzed and metal catalyzed in this hydrogenation reaction? Does it affect the product of the reaction?
Okay, thank you very much. Okay. Okay.
Yeah.
Can I answer now? Okay.
Yeah.
So thank you very much for the question. So there is when we talk about heterogeneous catalysis, there's always two parts that we have to remember. First is the metal is our active center, and also we have a support. This support can be metal oxide or zeolite, okay, or silica. Okay, the difference is why you said use metal oxide instead of metal catalyst. We use metal catalyst. Palladium is our metal catalyst, and then it become alloy when it reduced with zinc oxide to become palladium zinc alloy, which is what we investigate as our main active species. Metal oxide is still very important as our support. So when we talk about CO2 hydrogenation reaction, to have this metal oxide is very important, or any metal support to improve the CO2 absorption as a site for CO2 absorption. Yes, we still need metal and we still metal oxide. There is a synergy between this metal and metal oxide. Okay, and then what is the difference between metal oxide and metal catalyst? This is what I mentioned. So metal is the site for hydrogen dissociation. So remember that we have carbon dioxide and hydrogen gas. Okay, hydrogen gas need to be dissociated into hydrogen atoms in order for reduction to occur. This dissociation of hydrogen is occur on palladium metal or palladium zinc metal alloy. Okay, but CO2 absorption occur on your metal oxide. This is normally metal oxide provide oxygen vacancy site that can interact with the CO2 and then weaken the bond and will be much more easier for hydrogen to reduce them. So this is the different role of metal and metal oxide support. Does it affect the product of the reaction? Yes, it affects the product of the reaction. The reason why it affects the product of reaction, because the surface basicity might be different depending on the type of metal oxide that you use, and then the orientation of CO2 when it absorbs on metal oxide will be different depending on the basicity of the metal oxide support. And also the selectivity also different. I'll show you at the very beginning of my talk, when we have titanium and alumina, we started to produce methane instead of carbon monoxide and carbon dioxide and methanol. This is because it related to the ability of titanium and alumina to actually promote methanation reaction rather than hydrogenation reaction. Yes, metal oxide support will have this significant effect on the activity of the metal catalyst that we use. Thank you very much. I hope it's clear.
Okay.
I hope I answered your question. Yep.
Okay. Is there? Okay, there is 2 questions more. That's from our colleague here. There are several synthesis methods for bimetallic catalysis. Based on your research or your experience, which is the strength and the weaknesses method? Yeah.
Okay. From my research that I discussed just with you now, I've produced, the catalyst that we produce is using impregnation, salt immobilization, and also another one is we use chemical vapor deposition. All these methods have their own benefits and also disadvantages. The impregnation method, the benefit of impregnation is very easy to do, which is basically you just mix the catalyst, dry them, and calcine them. But the problem with impregnation method is your catalyst tend to sinter. So when we reduce the catalyst up to 700, you can see that there is an enlargement of nanoparticle size up to 30 nanometers. So when we test the catalyst produced by impregnation is not active at all when we reduce at high temperature. So this is the disadvantages of impregnation method. It's prone to sintering at high temperature. And then we also have salt immobilization method. The benefit of salt immobilization method is we can control the particle size of palladium that we produce, which is we have a very small nanoparticles up to 2 nanometers. Now, when we have these 2 nanometers in size, we can actually produce this catalyst that has high selectivity to methanol. The problem with salt immobilization method is it very difficult to produce, which is you require reducing agent, sodium borohydride, which is not really pleasant. And then you have this PVA as a stabilizer, which if it is too much, it actually can start to poison the surface of palladium. Another thing is you can only produce palladium zinc alloy, palladium on zinc oxide support. You cannot try to put palladium zinc alloy on titanium or alumina. This is because zinc is not stable under reducing agent. When we try to put sodium borohydride and the PVA as a ligand, the zinc will actually reduce and cannot be stabilized by PVA, and it just drop at the bottom of the beaker. So salt immobilization method, although it's very efficient to reduce, to form a very small nanoparticle size and high activity, you cannot use salt immobilization method to produce palladium zinc alloy on different type of support other than zinc oxide. And lastly is chemical vapor impregnation. We really like chemical vapor impregnation because you can create palladium zinc alloy on any type of support. You can use titanium, alumina, ZSM5, silica, any type of support. And it's non-solvent, which is you don't have this messy wet chemical in your lab. And it's basically a combination of palladium palladium acetyl acetonate, and zinc acetyl acetonate, and then add under vacuum at 145 only, and then there's a reaction between the ACAC precursors together, and then actually create this palladium zinc alloy. It's much simple, but at the same time, it gives a promising results to create small palladium zinc nanoparticles. There's 3 main methods that we use to produce palladium zinc alloy. All of them have benefits, all of them have the disadvantages. It depends on what you want to achieve in your experiment. Thank you.
Okay, it's the last question, but it is already asked in the previous. So we change this the other one. as we know that palladium metal is one of the material that is quite expensive. For large scale, is it possible to use palladium-based catalyst for industrial application, and what's your suggestion?
Okay, we always talk about how expensive precious metal is. Yes, palladium is expensive, gold is expensive, but when we talk about heterogeneous catalyst, okay, we doesn't need a lot of this metal. We only have like at least 5%, normally 5% of this metal, one. And heterogeneous catalysis is actually very stable. You can use it again over and over. And there's always a method for us to improve the activity after a long period of time. Basically, they are very sustainable, even though the price is expensive. Can we use noble metal for industrial application? Of course, there is a quite recently from our group in Cardiff University that they actually produce gold nanoparticle catalyst for formation of vinyl chloride monomer for polymer industry, which is replacing the mercury that is commonly catalyst that have been used for that kind of industry. Yes, if you produce a noble metal catalyst, even though it's expensive, but the profit that you generate is very high and it's very environmentally friendly. Of course, there is no reason why precious metal cannot be used in industrial application. Yes.
Okay, I thought that's really interactive communication, yeah, from the participants through chat, and the time is already finished for us. And thank you very much for your presentation, Dr. Hasliza. And
thank you very much.
Also, thank you very much for the participant who attend this plenary session. Thank you very much again, and see you in the parallel session.
Thank you, Lisa.
Okay, well, thank you so much to our moderator, Bapak Zulfikar PhD, and our honorable keynote speakers for your wonderful insight in current science and its applications. Then we will move to the next session. Ladies and gentlemen, for your information, our next agenda is parallel session. There are 2 parallel sessions for this afternoon and 2 next parallel sessions for tomorrow morning. And in today's first session, we will have 4 invited speakers in each parallel room to talk about the current research on chemistry and material science. So if you want to see the detail of the schedule, you can check it on our website and also our booklet, Book of Abstract. It is also suggested for you all that have role as oral presenters to check your own schedule in our conference Book of Abstract. So hopefully you will not miss your own turn on parallel class. We would also like to inform that the presenter must still stay in the parallel session, also for Q&A session, even though the presentation will be presented by video. The form of video presentation will not reduce the essence of the presentation and provides the opportunity to all participants to present their best. So your presence in the parallel class is so important. When you are not in the parallel class during your turn or your schedule, then your video for oral presentation will not be presented. And it means that committee cannot provide you a certificate for oral presenter in the end of this conference. So we encourage you all, the presenters, to be active and available in your parallel class in order to make the committee easier in collecting the data of your presents. As the committee requested before in the chat room, please rename your Zoom profile during the parallel class using the format EC chair ID number _ your name. If you have any question, you can ask the committee anytime. But before we move to parallel session, we will have a lunch break for about 1 hour. Hopefully after that you can rejoin us in parallel session freshly and enthusiastic. For the link of each parallel class that you can join would be sent in the Zoom chat room. I think that's available now. Or you can see it in our book of abstract. Okay, I think that's all from me. Thank you so much for your attention in joining us this morning. Stay healthy, keep your spirit. See you later in the next 1 hour for parallel session. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.